It begins in a hush that is not silence, but distance. Out where the sun is only a rumour, where night is the default and light has to argue for its place, something small carries its own patient momentum. It slips across the cold like a thought that will not let go. The black holds steady, then a grain of brightness registers, not in an eye but in a sensor, a pixel nudging upward against the background of random noise. That tiny insistence is enough. The cosmos says little. The instrument listens anyway. Hearts do not quicken in observatories. Calculations do. A set of coordinates is paired to a time, then checked against the moving skeleton of known bodies. The object is not on any list. The parallax between frames refuses to fit a familiar ellipse. The arc, even in coarse numbers, leans outward with a confidence that does not belong to anything born here. It is not a neighbour coming home to the Sunday. It is a passer-by, a traveller that learned long ago how to refuse invitations. Its name arrives as a convenience for conversation, a label that lets minds gather around the same map. The letters feel human, the motion does not. It carries speed that was assembled far from this gravitational well, a speed that grants it the luxury of indifference. No matter what attention it attracts, the trajectory is already composed. The visitor will skim the light, take its measure, and go. Between numbers and narrative, a question hardens. What is the worst that could happen? Not because drama is the point, but because caution is a form of respect. Space has very few catastrophes that look like stories. Space has accumulations, small forces added over long distances, grains colliding with ideas, statistics shaping what is possible. Worst case here is not an apocalypse sung in fire, but a boundary traced in probability, a contour map of rare circumstances. The map still matters. As the stranger brightens, sunlight begins its old conversation with ice. Energy meets molecules that have slept for eras, and the molecules answer by lifting away. The answer is visible as a faint coma, a blur wrapped around a dark core that refuses to show its face. Dust learns to follow gas. Gas learns to follow heat. The whole fragile thing paints a filament across the sky, a whisper drawn with particles. In that filament is a biography, written in chemistry that reflects a nursery no one here remembers. A camera on a mount follows the predicted sky position. It does not blink. Humans do. The frame drifts across a sprinkling of stars, then stops. The faint smear is there again, offset as the model suggested. The exposure ends. Another begins. Uncertainty shrinks. Just a little. The smear is real. No rumour survives a sequence of confirmations. The visitor is now a fixture for the season, a point that will gather attention as it approaches a sun that takes curiosity and turns it into heat. Risk does not enter as panic. It enters as responsibility. Engineers think in terms of distances and shields, in terms of orbital traffic and sensor health. A tail made of dust can become a veil that scatters light into instruments that prefer contrast. Grains invisible to the eye can strike fast enough to pit metal. Ionized gas can talk to magnetic fields and make plasma behave like weather. None of that is dramatic at a single moment. All of it has consequences when missions depend on precision. So a question becomes a checklist. Stories like comets are often treated as omens in the folklore of small worlds. Here the omen is a reminder to measure better. The math is conservative and exacting. Angles are refined nightly. Brightness is watched for changes that signal activity. Models evolve to fit the data that stubbornly grows. Best case is knowledge. Worst case is surprise. The difference between them is attention. In attention there is also awe. The nucleus, hidden and lightless, is an archive that never meant to be read. Its surface has been auditioning for sunlight since before the present arrangement of continents existed. It may carry a crust that remembers the chemistry of another star's childhood, a balance of ices that were common there and odd here. The coma, faint and honest, is the one translation anyone gets. It writes in emission lines and in colour, and those lines have dialects. Those dialects challenge the assumptions that grew comfortable in familiar skies. There is a humility to calling it a stranger. It is not strange to itself. It is a product of collisions, freezes, radiation storms, long winters between stars. It has encountered dust clouds and the pale tides at the edges of systems. It has coasted through the electric breath of suns uncounted, always saving enough of its speed to avoid capture. That history is carried in every flash of light it reflects, in every molecule it lets go. The tail is a sacrifice made to time. The path is a signature stamped into the frame of the solar system, and then beyond it. The art of watching becomes the art of waiting. Calendars grow new marks. Telescopes schedule precise glances that accumulate into a portrait. The portrait is not a face. It is a set of constraints, curves that enclose the truth more tightly each night. The mind learns to draw confidence from shrinking ellipses on a plot. The heart, if invited, learns to sit quietly and let the distant thing be itself. Wonder is not loud, it is disciplined. There is a romance to escape velocity that is not sentimental. To carry enough motion to ignore the sun is to have been launched by a story with violence in it, a scattering event worth a quiet respect. The visitor is a survivor of a past that does not offer commentary. It keeps the terms of its origin to itself. It allows only inference. That is enough. Inference in the hands of patient minds becomes a kind of telescope that looks not only outward but back in time, toward the architecture of alien disks and the outskirts of unfamiliar gravity wells. A planet lit by cities will not notice the visitor with naked eyes from most places. The discovery lives in images calibrated against darkness, and in numbers that live happily in spreadsheets and code. The grandeur is in restraint. That restraint serves safety too. Worst case is explored without performance. If dust grows dense, the models will say so. If jets become unruly, the curvature of the path will whisper the change. If anything resembling risk rises above background, there will be time to act at the scale that space permits. Children trace arcs with their fingers on posters. Scientists trace arcs with parameters on whiteboards. Both gestures point to a future position where the stranger will be closest to the sun and then closest to the earth at some modest distance. Closest is still far. That word is a trick of perspective. It is also a comfort. The numbers that matter sit between two realities, the human appetite for story and the cosmic refusal to bend to that appetite. Precision connects them without letting either one dominate. When light reflects from that small body, it brings with it a flavor. The spectrum is a chord played on ice, rock, sunlight, and motion. The chord changes as heat changes, as jets open, as spin reorients, as crust responds to stress. Listening to it is a discipline that feels like listening to weather. The sky speaks in patience. The instrument answers in patience. Between them, they refine the portrait until the stranger is not so strange anymore, only specific. The worst case is finally a boundary drawn around ignorance. It is a way of saying that fear has to be quantified to be useful. The object does not care about the boundary. The boundary protects those who care for machines and missions. For antennas that have stared for years without needing to blink, it protects the fragile art of looking. The cost of that protection is attention, the currency already being spent in long nights and cold rooftops, in remote controls that move domes under clear air, in code that sifts noise to find a story. When the visitor writes its thin white question across the dark, the response is not panic but inquiry. The question is not accusatory. It is a presence offered at high speed, a chance to learn about what lies between stars by meeting what survived the journey. The answer will be complicated and likely gentle. The process of earning it will demand care. Somewhere above an ocean, above a desert, above a city that sleeps between streetlights, a sensor takes another exposure. A pixel brightens. The story continues to be written in units of light and time. The night over Rio Hurtado begins with automation, not ceremony. At El Source Observatory, the Atlas Chile telescope wakes, checks wind and humidity, then draws a grid over the southern sky. Its 0.5-meter Wright-Schmidt optics and wide 7.4-degree field drink starlight in 30-second mouthfuls. Each exposure is paired with another minutes later, then a third and a fourth, so motion can be measured rather than guessed. The camera reads out a square of 10,000 by 10,000 pixels, a quilt of numbers that will become decisions before dawn. The software knows the static sky. It subtracts a deep reference from each fresh image, leaving only what changes. Artifacts tumble out under a sieve of rules. Airplanes and satellites lose their disguise quickly. Cosmic ray scratches are thin and brief. What remains are points that move with a plausible rate and direction. The system groups them into tracklets, 4 dots in a straight line when seen from Earth's slow spin. The tracklets carry coordinates, times, brightnesses, and a first crude sense of speed. A learning algorithm assigns a score, a confidence that this is something real. One tracklet rises above the rest. The position is clean, the motion steady, the brightness consistent with an object that is neither too near nor too far. It is not on any list of planets, asteroids, or comets. Inside the pipeline, a temporary label is minted, a short code that means only this one, right now. A human at a console confirms the stamps of quality, then the alert leaves Chile and enters a global conversation. The candidate appears on a page watched by dozens of observers. A digital chalkboard where urgency is spelled out by a column called arc length. Minutes matter at first, then hours, then days. Telescopes in South Africa and Hawaii answer almost immediately. Each adds a brushstroke to a still fragile orbit, tightening the curve as the sky rotates. With 6 positions, the math becomes bolder. With 12, it begins to whisper something unusual. The best fit does not close. The preliminary eccentricity refuses to stay below 1. The line wants to be unbound. The flag that signals interstellar origin turns from maybe to likely as more dots are strung along the path. By morning in Chile, the observation arc has stretched across the planet's night. The minor planet center digests the measurements, checks them for bias, rejects outliers that do not share the same rhythm. An official notice formalizes what the network already suspects. The object receives a provisional cometary designation tied to the date and discoverer, then the letters that will travel with it through every future paragraph. The discoverer is the instrument itself, a system built to find things that might hurt this world, now pointing to something that only threatens ignorance. The site where it began is unassuming. A robotic pier and a small dome sit on a ridge of the Elqui Valley's dry mountains, where cold desert air favors astronomy and where power and data march up from towns that shine only faintly. The observatory code W68 is a shorthand used by professionals, a way to compress geography into 4 characters. The numbers behind those characters are precise, latitude, and longitude that tell the database exactly where photons were turned into measurements. The rest of the site's biography is technical. F. 2 optics to collect light quickly. Broadband filters tuned to balance depth and cadence. An image scale near 2 arcseconds per pixel, enough to follow slow motion without blurring too much of the sky. What looks simple in a press image is the end of a long story in design. Atlas was built to scan, to accept that most frames will hold nothing new, to keep working anyway. Its strategy is patience multiplied by electronics. Each telescope can map the visible sky at least once per clear night, and the network's geography fills in gaps left by weather and daylight. That relentless repetition is what allows faint wanderers to be separated from noise. It is also what allows a moving point to be tied to a second point and a third, because the cadence is fast enough that the visitor does not slip away between looks. Once the object is posted for confirmation, big mirrors turn. Gemini North tests color and sees a haze. The Very Large Telescope finds a slight elongation in longer sequences, a hint that gas or dust already lifts from a nucleus still too small to resolve. Hubble stares and returns a tidy tuft of light, a coma framed by stars that streak because the guiding follows the target, not the static field. Each new sequence returns to the clearinghouse, where orbit solvers harvest the positions and feed them to machines that can integrate gravity and time with a precision that keeps spacecraft safe. Naming follows rules meant to tame excitement. The cometary designation pins discovery to a calendar, then a proper name arrives that recognizes the system that spotted it. Only after the orbit is secure and the eccentricity has earned it, the interstellar prefix is granted. The number that precedes the I is a count of a short list, a way of admitting rarity with a single character. The full name carries a geography, a date, and a category woven into a single phrase that can be spoken without the weight of qualifiers. In the meeting rooms of teams that spend their lives preparing for unlikely events, the choice of words matters. The words are careful. The process draws strength from repetition, yet every discovery has its fingerprints. In this case, the precovery search reaches back into images taken weeks earlier by the same survey and by others. Faint smudges in those archives now match a predicted place within a chip's corner. Each successful precovery extends the baseline, trims uncertainties, and dilutes the chance that a quirk of geometry is fooling anyone. The arc grows from hours to days to months. With length comes clarity about where the object came from in the sky and where it will next appear. Human names can be attached to this narrative, but the work rejects heroics. Engineers keep them out smoother than weather would allow them to be on their own. Software writers chase bad pixels and bias frames with as much seriousness as any discovery announcement. Observers in small domes across 3 continents accept the tedium of repeating measurements so that 3 or 4 more digits in a coordinate can lock the orbit tighter. Managers protect budgets and nights of access so that a quiet routine can be interrupted by an urgent line of code that says, "Look here again." The place, the time, and the method are now tied together. Chilean desert air served the first seeing. Early July provided a sky position that was accessible from both hemispheres. The how is the union of high cadence, difference imaging, machine ranking, and a community that trusts the tools. When the internal alert rose above the threshold, it did so into a network that knew exactly what to do next. That knowledge was built on drills, on previous close calls that did not become headlines, on near-Earth objects that demanded focus for a night and then yielded to better data. The discipline transfers seamlessly to a visitor with no intention of staying. The moment of official recognition is strangely still. No crowd gathers, no ribbon is cut. A notice circulates, a database field is updated, an ephemeris page begins to fill with future coordinates. The tone is factual. The implications are left for others to explore. The telescope covers its electronics against the first hints of morning, parks the mount, and lets the dome close over its quiet heart. The next night will bring more of the same, more exposures where nothing happens, and perhaps a few where something extraordinary insists on being seen. Discovery means the object now exists in human time. Predictions tie it to dates and constellations. Finder charts appear. Schedules shift. Instruments prepare modes that favor faint gas lines or dust continuum, depending on what is expected. Crowds will not gather on city sidewalks for this one, but observatories will find themselves full. The calm of the first detection, the chain of confirmations, the shape of a hyperbolic solution, and the name that records this entire process, together form a clear beginning. The mystery is now a map. The rest of the work will be to fill it with measurements and, if fortune permits, with meanings that reach beyond the numbers. The architecture of motion in a stellar system is written in conic sections. Circles are the polite ideal. Ellipses are the real compromise that binds planets and most comets. Parabolas are the delicate threshold between staying and leaving, a portrait of zero excess energy. Hyperbolas are the refusal to belong. The curve that arrives with positive specific energy carries a fact that does not yield to sentiment. It will not close. No amount of sunlight or attention will persuade it into a loop. Astrometry takes the lead. Each measured position is paired to a time, and the fitting machinery searches for the conic that best threads those needles. Small arcs can deceive, especially when the tug of giant planets distorts the picture in a heliocentric frame. The careful test shifts the reference to the solar system's barycenter and asks a stricter question. Does the orbit remain unbound when projected beyond the realm where planetary perturbations matter? The answer that persists through more data points and longer baselines is the one that matters. The numbers describe a hyperbola with eccentricity comfortably above 1 and a semimajor axis that is negative by definition. In that language, negative means freedom. Energy tells the same story with fewer nouns. The vis viva equation ties speed and distance to the sun's gravitational parameter. Where a bound traveller yields a negative total specific energy, this path sits above zero by a margin that does not vanish under improved calibration. The symbol V infinity becomes a character in the narrative, the asymptotic speed the object would carry far from solar influence. That speed holds its own against measurement errors and against the subtle pushes of outgassing. Gravity bends the path but cannot claim it. Capture is a word that tempts the imagination and resists the physics. To turn an unbound guest into a resident, energy must be dissipated. Gas drag exists only in fantasies of an early nebula. Collisions are so improbable that they drift toward fiction. Planetary flybys can trade energy, but the bookkeeping is strict. Without a massive atmosphere to brake against, or a very specific chain of encounters, the sun remains a lens rather than a net. The orbit will kink, not close. The turning angle is a function of impact parameter and V infinity, and here that angle remains modest. The curve will lean inward, salute the light, then lean outward with almost the same indifference it brought from interstellar space. Long-period comets from the distant reservoir near the system's edge often masquerade as parabolic because their eccentricities are so close to 1. Many are technically bound, their semi-major axes measured in tens of thousands of astronomical units, and their periods longer than written history. Their inbound energies hover just below zero. Planetary kicks can push some onto temporary heliocentric hyperbolas, yet when the orbit is computed in barycentric terms before the close approach, the signature usually softens back toward the parabolic limit. That diagnostic separates a native wanderer from a true outsider. In this case, the outsider remains an outsider no matter how the frame is chosen. Outgassing introduces another layer of complexity and an opportunity for misreadings. Jets of sublimating ice can provide small non-gravitational accelerations. These are modeled as radial, transverse, and normal components whose strengths evolve with distance from the sunday. For some comets, the correction is essential. A misfit that looks like a hyperbola can be pulled back toward a near parabola when jetting is included. Here, even with conservative allowances for activity, the positive energy survives. The delta V available from sunlight-driven venting cannot pay the debt required to bind the path. It can tweak the heading, not rewrite the chapter. Inclination adds to the sense of otherness. Most planetary bodies keep near the ecliptic, a thin disk where the solar system keeps its largest accounts. A steep or even retrograde approach slices that disk at an angle that speaks of an origin not obliged to our geometry. The argument of perihelion and the longitude of the ascending node plot, a trajectory that does not owe much to the usual gravitational family politics. It moves through the planetary neighbourhood like a tourist who speaks a different grammar, yet follows the universal rule of mass and distance. The TESS parameter with respect to Jupiter is another quiet discriminator. For Jupiter family comets, it hovers near a characteristic range shaped by 3 body dynamics. For high inclination interlopers, it drifts far from those values, signalling a dynamical class that has not been sculpted by repeated encounters with the giant planet. It is a numerical way of saying that this visitor has not paid the tolls of residence here. That conclusion sits beside the hyperbola and harmonizes with it. Uncertainty maps are part of the craft. Confidence ellipses around each predicted position shrink as nights accumulate, and the corridor of possible futures narrows. The corridor never touches any planet closely enough to change the story. Integrations that push the solution backward in time show no encounters in the outer system that could have supplied the necessary energy. Instead, the path coasts in from beyond the planetary magnetospheres, as if a long rail delivered it from a careless throw in another system. Numerical experiments that spray clones through software solar systems yield outcomes that differ in detail but preserve the central fact of non-membership. The shock is not theatrical. It is the discipline of finding a rare case that forces the local rules to admit they are local. Gravity still rules, but its empire has borders. The sun can bend a trajectory without owning it. A body with the right asymptotic speed treats this star as a brief curvature in a longer line. That perspective changes how astronomers allocate attention. The window for learning is finite and known in advance. The arc through which brightness rises and falls is written into the geometry. There is no second chance on another revolution. Origin stories are inferred from motion before chemistry has a say. An unbound path implies ejection by gravitational scattering near another star, perhaps by giant planets in a youthful system, perhaps by a binary companion that ran out of patience. In dense birth clusters, passing stars and tides hasten the eviction of planetesimals. The result is a population that wanders the interstellar medium with speeds informed by the velocity dispersion of their nursery. When one happens to cross the solar system's front yard, its track announces that deep history without sentiment. The orbital parameters are a fossil written in algebra. The practical consequences of a hyperbolic trajectory are simple. There is a closest approach to the sun that will happen once, a closest approach to Earth that is modest, and then a monotonic fade into the outer dark. Mission planners can sketch timelines with unusual confidence. Risk assessors can draw lines that separate what is imaginable from what is not. The object is fast, but not so fast that nothing can be measured. Slow compared to light, fast compared to habit. The cadence of observations is matched to that pace, and the accumulation of knowledge is paced to a countdown that gravity itself provides. Even the vocabulary carries a kind of poetry. Eccentricity greater than 1, negative semi-major axis, positive specific orbital energy, non-zero v infinity. Each phrase sounds like a verdict. Each verdict protects against wishful thinking. There is satisfaction in such clarity. The visitor remains a visitor. The sun provides a spotlight, a stage, and a schedule. The curtain will fall at a time the equations already foresee. First light looks like a rumour. A faint puff sits on the star field, a blur just wider than the point spread function. The raw frame is noisy, but the radial profile refuses to match a star. Subtract a stellar template and a soft residual remains. Circular close in and slightly lopsided farther out. The asymmetry is modest yet persistent across filters. It is the kind of misfit that causes quiet pauses in control rooms. Something is venting. Teams stack images to deepen the signal. Guiding follows the moving target so background stars smear into arrows while the object stays tight. In the deeper composite, the coma reaches a few tens of thousands of kilometers. Dim but honest, fading with radius more slowly than the canonical law for a steady outflow. The photometric slope hints at large grains that do not feel radiation pressure as easily as fine dust. A linear tail is difficult to defend, but a shallow brightness enhancement points roughly anti-solar, refusing to sharpen into the familiar spear seen from brighter comets. The geometry is real yet undecided, like handwriting at the edge of visibility. Broadband colours add a sketch of personality. The flux through a blue filter is suppressed relative to red, a gentle reddening consistent with a dust mix seasoned by space weathering. The colour is not extreme. It suggests a surface or coma population that carries complex organics and small silicates. Nothing outrageous, but the ratio varies with aperture radius, which implies gradients. Closer to the centre, the light is slightly less red, a sign that fresher material is rising from the nucleus and aging as it drifts outward. The gradient is a first hint of a breathing pattern. Photometry with small apertures searches for rotational modulation. The light curve wanders by a few hundredths of a magnitude over hours, enough to tempt a period fit, not enough to declare one. If the nucleus is elongated, spin should inscribe a rhythm on the brightness. Gas and dust blur that rhythm. A provisional period emerges from a Lomskargel analysis, then retreats when another night refuses to support it. The conclusion becomes a caution instead of a number. The nucleus is likely spinning, perhaps in a complex state. Jets, not just shape, may be sculpting the light. The absolute magnitude derived from early distances gives a loose upper limit on size. Assume a dark cometary albedo, and the unresolved nucleus cannot be much larger than a few kilometers. Adopt a brighter surface, and the size shrinks. Either way, the core hides comfortably below resolution. That invisibility is typical and still disquieting. Most of what is seen is coma, a conditional glow that depends on sunlight and activity. That dependence means the look of the object can change without warning if a crust fissures or a jet ignites. Syndine and synchrone diagrams come into play. Investigators overlay families of model dust paths on the images, each curve representing grains of a given size released at a given time. The fit is not clean. No single emission epoch can explain the spread. The best compromise points to a gentle, ongoing release of various sizes rather than a single burst. Radiation pressure should bend the smallest grains into a graceful sweep, yet the measured position angle of the faint enhancement resists easy alignment with the antisolar vector. Either the ejection is anisotropic, or the signal is too weak to convict the physics. Both possibilities keep astronomers awake. A coma that brightens more slowly than expected complicates the narrative. Many comets obey an empirical law in which brightness scales roughly as a power of heliocentric distance. Here the slope is shallow. Production rates inferred under standard assumptions are lower than the visual impression suggests. The coma may be dust-rich and gas-poor, or gas may be present but dominated by species that do not radiate strongly in the chosen filters. The choice of continuum bands was deliberate, yet the object translates in its own dialect. Gas seekers pivot to narrowband filters. A search for cyanogen and diatomic carbon returns limits rather than detections. Every clear night improves the limits, tightening the arithmetic of what can be hiding. The null result is a clue. Either the volatile budget favors other molecules or the active areas are too small to lift the usual carbon species into measurable columns at this distance. The absence outlines the presence of something else by negative space, like a sculpture chipped from marble that reveals a form by removing what is not. Morphology reacts to phase angle. As the sun-object observer geometry evolves, forward scattering can surge the brightness of dust viewed near zero phase, or suppress it at larger angles. The observed phase function is mild, another suggestion that the grain population is skewed to sizes that scatter more neutrally. Tiny grains would flare more dramatically with geometry. Bigger grains keep their poise. That poise, while aesthetically pleasing, hints at mass flux carried by particles that travel with inertia and resist shaping by light. Astrometry provides a parallel commentary. Residuals to the best fit orbit are small and evenly distributed, the hallmark of clean measurements, yet observers keep testing for subtle drifts that could betray non-gravitational forces. If jets push unevenly, the path will whisper it long before it shouts. Early data offer no such confession. The doubt remains, a standing question held against future nights. Microspectroscopy on large telescopes looks for dust features in the near-infrared. The signal is meagre, but there is a hint of a broad plateau rather than a sharp silicate peak, perhaps a sign of amorphous constituents. If crystalline signatures appear later, they will talk about heat histories. For now, the spectrum is tastefully quiet, leaving modelers to explore families of compositions consistent with the colors and the lack of strong gas bands. No one trusts a single instrument. Aperture masks calibrate biases. Flat field phantoms are chased down. Star catalogues are cross-checked to ensure that reference magnitudes do not inject false color. Teams on different continents repeat the same observing sequences so that independent pipelines can reconstruct the same coma asymmetry. When independent stacks show the same faint lobe at the same position angle, confidence grows that the lobe is not a processing artifact. A small outburst could clarify or confuse. A sudden brightening by half a magnitude would push signals above thresholds and reveal jet structure. It would also reset baselines and scramble planned sequences. For the moment, the object behaves with restraint. Its caution gives time for deliberate work. Finder charts are refined. Exposure times are tuned to hold the moving target against trailed stars without smearing away the very features that justify the effort. Amateurs with modest telescopes contribute stacks that reach surprisingly deep. Their images, taken from suburban backyards and mountain turnouts, fill gaps in cadence that big facilities cannot cover. The best of these contributions show the same soft coma and the same unenthusiastic tail. Some display faint striae that could be image artifacts or real structures. Professional teams reach out quietly to verify. The shared sky becomes a temporary laboratory where each participant plays a specific role. What began as a single detection is now an early portrait with unfinished edges. A small nucleus hides inside a glow that refuses to behave like a template. Dust seems plentiful and somewhat coarse. Gas signatures traditional to comets are muted. The faint tail orients near the antisolar line but lacks conviction. A color gradient suggests fresh material near the source and processed grains farther out. A rotational period refuses to settle. Every fragment of evidence is plausible on its own. In combination, they set the stage for questions that instruments tuned to chemistry will soon address. For the moment, doubt is a virtue. The object is neither anonymous nor understood. Its face is an unresolved point wrapped in a mood. The mood is the geometry of a coma that hints and withholds. The first glances do what first glances should. They replace ignorance with uncertainty that has shape, tone, and direction. From that uncertainty, better experiments can be designed and better nights can be scheduled. What looks like hesitation is the discipline of not telling a story the data have not earned. A spectrum does not shout. It murmurs in bands and edges, in slopes that tilt by fractions, in lines that rise just above the noise. When the light from the coma is unravelled, the pattern refuses the familiar script. The continuum is warm with dust, gently red, but the gas signatures do not lead with water. Instead, the deep infrared carries a broad shoulder where carbon dioxide breathes, a presence so strong that any attempt to treat it as secondary collapses. The usual choir of cyanogen and diatomic carbon remains faint. The ladder that points to hydroxyl, the proxy for water, is hesitant. Chemistry steps forward with a posture that overturns expectation. Most comets near the inner system lean on water as their central engine. Water sublimates with a confidence that rises steeply as sunlight intensifies. Carbon dioxide adds a supporting role, and carbon monoxide becomes important farther out where cold rules. Here, the order has been rearranged. The ratio of carbon dioxide to water is inverted, a dominance that persists across nights with different instruments and different reduction methods. It is not a numerical quirk rescued by calibration. The spectrum keeps returning to the same answer, a budget that places a heavier share of volatile labour on carbon dioxide. Thermal physics gives the first explanation to TESS. The surface might carry a tight crust, a compacted mantle of dust, and irradiated organics that locks water under a seal. Carbon dioxide hides deeper in many cometary nuclei, yet it sublimates at lower temperatures than water. If the mantle is fissured just enough for CO2 to percolate through microfractures while water remains trapped, activity can begin early and stay CO₂-rich even as distance falls. The thermal wave from sunlight only penetrates to certain depths per rotation period. If volatile layers sit at different depths, the timing of their release splits into distinct seasons measured in kilometers of travel rather than months. Structure inside the nucleus could amplify the inversion. Poor distributions decide which molecules find highways to the surface. A labyrinth of capillaries with sizes tuned by ice sintering might favour the passage of lighter, more volatile molecules, while restricting the heavier flow of water vapour. Gas drag at the vent thresholds then selects dust grains by size. Coarse particles that feel radiation pressure weakly can still be lifted by dense carbon dioxide flows, creating a dust-rich coma that masks weak emissions in some bands. The visible impression of activity becomes unfaithful to the gas composition, a masquerade that only the infrared unmasks. If chemistry is destiny, origin becomes implicated. A body with such a lavish carbon dioxide budget could have formed near a snowline where CO2 condensed efficiently, closer to its host star than the zone where carbon monoxide would dominate, but farther than the waterline. Disks around young stars are not uniform. Temperature gradients, pressure bumps, and evolving UV fields create rings of preference where certain solids accumulate. A fragment born in a region where carbon dioxide ice was abundant, then later ejected by giant planet migrations, would carry a pantry unlike the pantry familiar to local comets. That story would naturally write a CO2 forward spectrum. Non-gravitational forces emerge from this chemistry with new leverage. Carbon dioxide jets can produce torques that spin a nucleus faster than water-dominated jets at the same total mass flux, because the onset distance is larger and the active season longer. A nucleus that began its journey with a comfortable rotation state can be coerced into a complex tumble as vents switch on and off under a moving sundae. Spin-up is not merely an academic metric. If the period shortens past the structural endurance, fissures widen and surface plates shift. In brittle aggregates, the end point is fragmentation. Fragmentation seeds a cloud of centimetre to metre-sized pieces, each with its own microjetting and its own path. That cloud becomes a temporary archipelago that spacecraft would be wise to avoid. Carbon dioxide behaves differently in the plasma environment as well. Ionization leads to CO2+ and its daughters, feeding a chemistry that modifies the local ion tail and the pickup of particles into the heliospheric flow. The interaction can disturb radio observations and complicate in situ plasma measurements for any probe that approaches. In the worst modelling branches, strong CO2 release combined with large grains generates a wide dust fan intersected by energetic plasma boundaries near the heliospheric current sheet, a stew that can scatter charged particles and drape magnetic field lines in ways that make remote sensing less straightforward. The hazard is not existential, it is operational, yet operational fragility is where many ambitious missions can stumble. Observationally, confirmation of low water is perversely hard from the ground. Earth's atmosphere is full of water lines that carve gaps through key wavelengths. Space-based instruments can target the 2.7 micron band of water and the 4.26 micron band of carbon dioxide cleanly, yet telescope time is finite, and weather in space has its own logic in the form of scheduling and instrument constraints. Analysts resort to proxies like hydroxyl emission in the ultraviolet, a chain that requires careful modelling of photodissociation and radiative transfer. If dust continuum subtracts imperfectly, faint gas signatures drown. The resulting error bars become a landscape where bold claims should be placed carefully. Even with caution, the trend remains. Carbon dioxide is calling the tune. The dust itself keeps secrets about the gas beneath it. Particle size distributions inferred from colour and from the shape of the phase function imply grains that are larger than typical, with a tail of small particles suppressed. If the venting gas is carbon dioxide, higher momentum density in the flow can loft heavier grains from a given throat diameter. Those grains fall back less readily, shaping mantles around vents and creating dunes of regolith that rework the landscape as the nucleus rotates. Patterns of deposition and erosion alter the future of activity by burying some sources and exposing others. Over time, the chemistry at the surface can appear to evolve even if the bulk composition remains fixed, simply because the architecture of escape is changing. There is also the possibility that the carbon dioxide is not primordial. Radiation in interstellar space can process water and carbon-bearing ices into more complex molecules and into trapped gases. Cosmic rays carve tracks through ice lattices and encourage the formation of CO and CO2 inside pores. When heating begins near the sun, these products can be released in pulses that mimic a native excess. Differentiating inherited composition from processed composition demands a full inventory of other species, including those that would be destroyed or altered by long irradiation. That inventory requires sensitivity often at the edge of what instruments can promise for such a faint target. As distance shrinks, one expects the water to wake decisively. If it remains slow to rise, several inferences compete. The mantle could be thicker than supposed, perhaps a centimetre-scale armour baked by millennia of cosmic winter. The active fraction of the surface might be very small, with only a few vents connecting to volatile rich pockets while most of the terrain stays dormant. The nucleus might carry a low bulk water fraction overall, a radical but not impossible architecture for a body formed in a different disk. Each branch of explanation has a different consequence for dynamics, brightness evolution, and the likelihood of breakups near solar heating. Risk models absorb these chemical choices and translate them into numbers that matter for hardware. A CO₂-led regime implies earlier onset of activity and broader arcs of dust exposure along the trajectory. Satellites far from Earth are unaffected unless their paths cross the wide, faint fans that can extend tens of millions of kilometers. Scattered grains at millimeter scales can pit surfaces and degrade star trackers. Spacecraft designers budget for such sandblasting near known active comets. An interstellar source with unpredictable chemistry demands wider margins, more conservative approach geometries, and careful mapping of dust isophotes before any daring close pass is considered by future missions. What deepens the mystery is not a single anomaly, but a suite of coherences that point in the same direction. The coma's colour and slope fit a dust-heavy release. The faintness of traditional carbon bands aligns with depressed water signals. The infrared welcomes carbon dioxide with unusual vigour. These clues support each other without collapsing into certainty. A disciplined patience becomes the strategy. More spectra will sharpen ratios. More nights will reveal whether water finally takes the stage, and careful photometry will catch any torque-driven changes in spin that hint at internal tension. Chemistry has turned a visitor into a thesis. A small body, silent to the eye and brief in our neighbourhood, carries a recipe for worlds that coalesced under different rules. That recipe is read in molecules escaping to sunlight, in grains dragged along for a ride, in the faint lines that record energy states flickering as photons are absorbed and released. The uneasy dominance of carbon dioxide expands the boundaries of what a cometary nucleus can be. It also widens the envelope of possibilities to watch for. From serene passage to unstable shedding, knowledge does not remove risk, but it draws a clear map of where caution belongs. Inside the nucleus, the heat budget is a quiet arithmetic. Sunlight falls, a fraction is reflected, the rest sinks into a foam of grains and ices. Thermal conduction crawls through that foam with the pace of a winter rumour. At a shallow depth, the daily temperature wave dies. At a greater depth, the seasonal wave dims to almost nothing. The difference between those depths is destiny. If volatile reservoirs sit above the diurnal skin depth, activity breathes with each rotation. If they sit below, the engine runs by seasons written in kilometres of travel and degrees of obliquity rather than hours. The material is not a solid crystal. It is a city of pores. Some are capillaries at micron scales, where gas molecules bounce more from walls than from each other, a regime where flow is governed by the mathematics of Knudsen diffusion. Others are caverns stitched by fragile bridges of sintered ice, a place where a small change in temperature can collapse an arch and open a path. Through that labyrinth, carbon dioxide migrates with a freedom denied to water if water ice has annealed into a tighter lattice. Gas that finds a throat becomes wind, wind becomes jet, jet becomes torque. Layering is not decoration, it is biography. Radiation in deep space etches the outer centimetres into a rind rich in complex organics and dehydrated minerals, a rind that is dark and mechanically tough compared to the interior. Beneath it, ice may be amorphous, a glass that once trapped volatiles in cages of disorder. Warm gently, and the glass relaxes. The trapped gases are freed in bursts that depend sensitively on temperature. If clathrate hydrates formed at some stage, Cages of water molecules lock carbon species until a threshold is crossed, then release them in pulses. Those thresholds serve as switchgear for the engine, turning vents on and off along latitudes and longitudes as sunlight crawls across a rotating shape. Geometry matters more than intuition allows. Concavities, pits, and overhangs focus sunlight by self-heating. A wall facing the sun radiates into a nearby wall, and the two share one another's warmth. The local temperature creeps higher than any one-dimensional model would predict. In such pockets, carbon dioxide finds ignition points far from the subsolar line. A vent there can maintain flow longer through twilight, leaning the jet off the expected radial direction. If the nucleus spins with a tilt, those pockets cycle through incubations that feel like seasons within seasons. With each cycle, material is excavated in arcs, forming scallops along pit rims and talus cones below them. The morphology is function written in relief. Porosity is both a path and a trap. Fine dust settles into voids as outgassing ebbs, sealing some channels and redistributing others. The seal may be partial, enough to restrain water vapor while still leaky to smaller molecules that hop through smaller throats. Over time, a differential permeability emerges. Carbon dioxide can escape where water cannot. The coma then records not only composition but plumbing. If pressure rises under a plugged cap, the cap can fail suddenly. An outburst ensues, lifting sheets of crust and exposing virgin ice. The engine surges, then chokes again as the debris falls back and blankets the wound. The cadence of these failures is a signature of strength and cohesion, quantities the eye cannot see but the dynamics cannot ignore. Tensile strength at cryogenic temperatures is a narrow margin written on brittle bonds. Laboratory analogues suggest that aggregates of frost and dust held together by van der Waals forces and sinternecks fail at modest stresses. A gentle spin-up can approach those stresses if mass distribution shifts subtly with sublimation. A nucleus that starts with elongated shape and uneven activity bears torques that increase its rotation rate. The threshold for surface shedding is reached when centripetal demand at the equator overtakes cohesion and gravity. Platelets drift, crevasses yaw, and the body answers with landslides in slow motion that spray grains into space. Each shedding event tweaks the inertia tensor, nudging the spin into precession or even tumbling. The engine does not merely drive jets. It rewrites the body's orientation to the sun, changing where heat arrives next. The subsurface is a parliament of ices. Water is the clerk, voluminous and stoic. Carbon dioxide is the member who speaks early. Carbon monoxide is the idealist who tries to speak from the cold benches farther out. If the object formed where carbon dioxide could freeze efficiently, that member holds many votes. It gathers in lenses and vanes at depths set by the thermal history of the parent disk. As tiny temperature gradients drive migration, CO2 lines these veins with frost. Reach a slightly warmer layer, and the frost reverses direction as vapor. Reach a vent, and it escapes. Over long time scales, migration can enrich certain latitudes or longitudes, setting up a geography of activity that has little to do with the present sun and much to do with paleoclimates written at formation. Grain physics completes the engine. Sublimation fronts do not carve smooth planes. They chew into the matrix along weak paths. The detached grains inherit momentum from the gas and their own mass from the crust. If grains are large, they barely feel radiation pressure and remain loyal to the velocity vector they were given. They fall back on ballistic arcs or hang near the nucleus in a bound cloud that thickens the local coma. If grains are tiny, they blow away and decorate space with the classic fan. The observed dominance of larger particles implies a pressure and throat size combination that favors heavy lift. That, in turn, points back to CO2-dominated jets, because their momentum flux per molecule can remain high at temperatures that are unkind to water. Thermophysical models turn these intuitions into maps. Take a shape model with pits and capes. Assign conductivity and heat capacity that vary with depth. Let porosity connect a spectrum of throats. Place reservoirs of carbon dioxide at layers whose depths are drawn from plausible formation scenarios. Then let the virtual sun walk around the virtual body while gas escapes according to local temperature and pressure. The model yields synthetic light curves, synthetic spectra, and synthetic trajectories of dust. Compare the synthetic data to reality, adjust, and repeat. In the simulation space, a cold engine with CO2 at modest depths reproduces muted water signatures, reddened dust continuum, and torques large enough to evolve spin on month scales. It also reproduces a frustrating trait: sensitivity to small uncertainties. Move a reservoir by a few centimeters relative to the skin depth, and the phase of activity shifts by many hours. The engine is exquisitely local, yet its behavior is cosmically visible. Worst credible branches live in the mechanics of failure, not in impacts. A cluster of vents near one latitude can synchronize through shared stress. As their jets align in time, the combined torque spikes. If that spike coincides with structural weakness at a specific longitude, a fracture can unzip across terrain that has been preloaded by centuries of thermal contraction. The unzip event produces a sheet fracture, ejecting slabs that shatter into multi-meter pieces. Those pieces begin their own short lives as minor cometesimals, each bleeding gas as sunlight touches them. A swarm like that is faint to telescopes, but real to any passing spacecraft. A minefield that drifts along the parent path for weeks. The engine has coughed, and the cough becomes a navigational hazard. A calmer branch still matters. Constant low-level CO2 outflow sandblasts the surface with re-impacting grains, eroding high spots and filling lows. The surface roughness changes the microphysics of heat absorption and shadowing, subtly increasing the fraction of light trapped in miniature canyons. That feedback raises local temperatures by a handful of degrees, sufficient to tip another pocket of amorphous ice toward relaxation. The release adds a trickle to the global outgassing, and the spin rate drifts a little more. Over a single apparition, the changes may be slight. Over decades, they can be decisive, setting the scene for a future approach where the engine's behavior surprises any plan that assumed stasis. Deep in the core, there may remain regions that have never known temperatures above a few tens of Kelvin. They sit as relics from a birth cloud, mechanically isolated by layers that have already cycled through many thermal seasons. Those relics are insurance against full exhaustion. Even if the surface becomes encrusted and activity wanes, a fissure opened by stress can connect a relic to the surface and rekindle flow in a place long dormant. In that sense, the engine is not a single machine but a district of machines. Many idle, a few active, all waiting on geometry. The lesson of such architecture is restraint in prediction and ambition in measurement. The cold engine is layered, permeable, sensitive to small causes, and capable of outsized mechanical consequences. It is not a bomb. It is a choir of valves whispering at the scale of pores and shouting at the scale of jets. Understanding it requires maps of heat, maps of porosity, and patient tracking of how a small body learns to aim its breath as it travels through changing light. In that restraint, there is safety. And in that ambition, there is the promise of translating a faint spectrum into the blueprint of an engine that was assembled under a star that is not this one. In some images, the brightness seems to lean toward the sun, a small wedge of light pressed against the upstream side of the coma. The intuition rebels because dust is supposed to stream away from sunlight, not into it. Yet near the nucleus, inertia has the first word. Grains leave vents with meters per second of freedom. For a few hundred kilometers, they travel along the direction they are thrown, while solar radiation pressure gathers influence only gradually. The result can be a compact sunward fan that sparkles with forward scattered light. Observers call this sunward snow, a fleeting glow where new grains glitter before the long push of light bends them downwind. Farther out, the physics reasserts the rule. Dust feels an outward acceleration that scales with the ratio of solar radiation pressure to gravity, a quantity encoded in the symbol beta. Tiny particles, with high beta, curve quickly into the antisolar tail. Larger grains, with small beta, resist the turn, and maintain trajectories only slightly deflected from their launch directions. A coma dominated by those larger grains will look calm, with a tail that is short, broad, and reluctant to sharpen. The same size distribution that makes the light curve steady also undermines the drama of a classic streaming tail. Geometry complicates the picture in ways projection can exploit. When the line of sight lies close to the object's orbital plane, dust that occupies that plane piles up in perspective. The sheet of particles, released over many days and spread thin in 3 dimensions, appears as a narrow spike pointing roughly toward the sunday. This is the antitail. It is not truly sunward in motion. It is a trick of viewpoint, a sharp filament formed where the eye looks along a dust sheet like a telescope peering down a hallway. An antitail is strongest when observers sit just above or just below the plane, so that the sheet becomes a razor at sky scales. Its appearance says less about defiance of radiation pressure and more about the discipline dust shows when it organizes along a plane. The gas behaves differently. Molecules ionized by sunlight are swept into a plasma tail that aligns with the solar wind and the interplanetary magnetic field. That tail is narrow, often straight, and frequently temperamental. Disconnection events can sever it when a magnetic sector boundary or a coronal mass ejection arrives. The severed segment flows away, while a new spine regrows from the nucleus. In an object with modest activity, the ion tail can be so faint that only long exposures reveal it, a whisper drawn as a thin blue line that pays no attention to the antitail's antics. Side by side, the 2 tails can point in nearly opposite directions, one honouring field lines, the other honouring perspective. The rotational state of the nucleus also sculpts the upstream glow, vents that face the sun near local noon launch particles into a headwind. As the body turns, those vents pass into dusk and night, but the grains they fired continue outward, then arc under radiation pressure to join the broader tail. If 2 or 3 active regions are spaced in longitude, their plumes overlap to form a small triangular fan on the sunward side that changes shape on the timescale of the spin. Short cadences can catch those changes as a breathing or flickering pattern that shifts in position angle by a few degrees over a night. The pattern is the handwriting of the engine, transcribed into dust. Models help separate these effects. The Finson-Probstein framework treats grains as mass points subject to solar gravity reduced by beta, and to radiation pressure pushing radially outward. Families of curves called syndines and synchrones map, where grains of a single size or a single release time will travel. Overlay those families on deep stacks, and the match, or mismatch, reveals whether the tail is produced by continuous emission, pulsed events, or a handful of favoured sizes. A sunward fan that refuses to align with early time synchrones, yet brightens at small phase angles, points to forward scattering and projection rather than to an exotic force. An antitail that strengthens as the viewing geometry crosses the orbital plane confirms the presence of a long-lived dust sheet. There is a practical edge to such diagnosis. A tail dominated by large, slow grains implies higher mass per unit brightness and longer residence near the nucleus. Those grains drift into a torus along the trajectory, a drapery that can persist for weeks. Spacecraft that pass through that drapery at tens of kilometers per second face millimeter to sub-millimeter impacts energetic enough to chip optics, scour radiators, and blind star trackers with momentary glints. Planners prefer to map the isophotes well beyond the obvious tail, because the faint wings of the dust fan are where risk hides. A narrow antitail flags the plane where concentration is highest. A sunward fan flags the vents that populate it most efficiently. There is also an opposite branch to consider. If the sunward glow is not dominated by dust, but instead by extremely fine grains carrying electric charge, Lorentz forces can play a role. Charged nanograins interact with the interplanetary magnetic field. Under certain field orientations, and for grains with beta near unity, an effective deflection can aim a subset of particles into curious arcs that briefly inhabit the sunward side before being carried off. The signature is a delicate, filamentary structure that does not persist night to night. It is a transient the size of small telescopes to medium telescopes, and it speaks of a chorus between dust dynamics and plasma that is usually drowned out by larger grains. Radiation pressure is not the only sculptor of light. Forward scattering by dust can brighten the sunward side dramatically when the phase angle is small. The coma acts like a screen made of tiny mirrors and lenses. At the right geometry, the screen throws an excess of light toward the observer, making a compact sunward wedge that outshines the antisolar flow, even when the mass budget is not particularly tilted. As the geometry changes, that enhancement can fade without any real change in the engine below. Without careful modelling, a changing phase angle can be mistaken for a physical surge or lull in activity. The worst credible optical confusion arises when an antitail coincides with a mild outburst. Grains from the outburst join the pre-existing plane sheet, momentarily sharpening the sunward spike and tempting fitters to infer a jet directly aimed at the Sunday. Follow-up nights usually resolve the error, but a single dramatic image can seed durable misunderstandings in public channels. The remedy is cadence. Sequences that chart morphology over hours to days capture the procession from sunward fan to antisolar tail, from spike to sheet, from illusion to architecture. Plasma introduces operational nuisances beyond visualization. Ion tails, when broad enough, can refract radio waves at long wavelengths and impose scintillation on signals from spacecraft that find themselves behind the comet as seen from Earth. The effect is subtle for faint objects, but worth modelling, because deep space navigation sometimes relies on radio links skimming through the heliosphere at shallow angles. A plasma sheet kinked by magnetic stress can act like a moving lens, imposing jitter on phase that confuses precise ranging. The hazard is not damage, it is noise at the worst possible moment for a trajectory correction. In the suite of possibilities, the backward tail is a teacher rather than a threat. It reveals where the orbital plane concentrates dust, pinpoints which latitudes are most active, and exposes the size distribution that matters for safety. If it sharpens and brightens, the inference is large grains and recent emission. If it stays faint and broad, the inference is older dust spread along the path with no fresh surge. Sunward snow adds a layer of nuance. Newly minted grains, glancing sunlight just so, briefly staging a counterintuitive display that disappears as physics remembers the hierarchy of forces. The geometry of tails is therefore not ornament but measurement. Each odd angle and fleeting spike encodes a clause in the comet's dialect. Listening to that dialect with patience turns confusion into a map. With that map, the search windows for dust are drawn more responsibly. Spacecraft keep their distance at the right times and angles, and the worst cases shrink from drama into manageable caution. The sky remains beautiful, even while it is being read as a manual. Expectation frames the question like a stage light. Near the inner system, water is supposed to be the actor who steps forward first, casting a familiar blue halo of fragments and fluorescence. Instead, the curtain lifts on a quieter set. The continuum glows with dust. Carbon species speak in the infrared. The cues that betray water are muted. Instruments begin to ask, not what is present, but what is hiding. There are several ways to count water without seeing it directly. One listens for hydroxyl at 308 nanometers, the ultraviolet fragment born when sunlight tears water apart. That line is bright in many comets, but Earth's atmosphere swallows much of it, and faint sources require space-based eyes. Another listens for radio whispers at 1,665 and 1,667 MHz, the ground state transitions of hydroxyl that can maser under cometary conditions. Even deeper in the spectrum, low vibrational bands near 7 to 3.1 microns carry signatures of water vapor hot enough to glow against the dust. Each method opens a door. For a reluctant target, each door lets in only a thin draft of certainty. A different approach steps sideways. Atomic oxygen emits narrow green and red lines when excited by sunlight and collisions. Those lines arise partly from water's children and partly from carbon dioxide's children. The ratios between the green line and the twin red lines act like fingerprints of parentage. If the red pair dominates, water has likely done the heavy lifting. If the green stands taller, carbon dioxide has taken charge. Even with a faint coma, those lines slip through darkness more readily than broad bands, offering a forensic route when direct water bands refuse to speak. Thermal models translate light into flux. For a small, dark body turning slowly, the equilibrium temperature at a few astronomical units from the Sun settles below the comfort zone for vigorous water sublimation. Carbon dioxide, with its lower sublimation threshold, stirs earlier. A simple energy balance tells the story. When absorbed sunlight cannot raise surface temperatures enough, water vapor pressure remains too small to drive a significant flow. Dust mantles only tilt the scales further by insulating the deeper ice, keeping the subsolar point cool in practical terms, even when the sun grows bold on the horizon. In that regime, water becomes seasonal rather than diurnal, waiting for a stronger sun or a thinner skin. The skin can be thin and still decisive. A few millimeters of compacted dust and irradiated organics carry low thermal conductivity. The daily heat wave dies inside them before reaching ice. Beneath the skin, a thermal lag persuades volatile layers to ignore the day's rhythm and obey the slower change with distance. If water ice lies deeper than the skin depth set by rotation, its sublimation front may be asleep while carbon dioxide migrates up through microfractures. In this architecture, water is not absent. It is embargoed by physics. The phase of water matters. Amorphous water ice, a glass formed at very low temperatures, can trap other molecules in its disordered structure. Warm it past a threshold and it crystallizes, releasing trapped gases and a small burst of heat. That transition is an ambush written into the material. A nucleus that carries amorphous layers can appear quiet long after carbon dioxide has begun to flow, then suddenly show a surge when the crystallization front reaches a depth where sunlight finally trespasses. In the language of observation, the coma that looked carbon-driven can pivot late toward water without warning, not because composition changed, but because structure remembered its own switch. Clathrate hydrates introduce a second ambush. These are cages of water molecules that imprison small gas molecules. Under the right pressure and temperature, clathrates remain stable, locking carbon species and others into a crystalline prison. Cross a boundary of heat and they dissociate, freeing their guests. The pattern of which gases appear, and when, becomes a diary of these cages rather than a simple inventory of original mixtures. If clathrates are present, the first abundant gas need not be water or carbon dioxide strictly by volatility. It can be the gas whose cages happen to encounter the thermal wave first. Observation has its own traps. Dust continuum is a generous light that hides faint gas emissions unless subtraction is precise. Fluorescence efficiencies depend on heliocentric velocity as well as distance, turning some orbits into favorable amplifiers and others into muting rooms. Slit orientations on spectrographs can miss narrow jets and sample only the calmer ambient column, depressing apparent production rates. Telluric absorption scars the near-infrared, asking for calibrations that punish time and patience. A null result for water in one geometry can soften into a detection when the same equipment rotates its angle across the coma or waits for a night with different air. If water is suppressed, grains can still carry its signature indirectly. Icy grains lofted from vents sublimate as they drift, creating a halo that cools as it expands. In scattered light, such a halo can flatten the color slope and introduce a subtle increase in polarization at small phase angles. Spectra may reveal the 1.5 and 2.0 micron absorption features of water ice in reflected sunlight if grains remain intact long enough. That tactic turns the question inside out. The coma becomes a transport laboratory where water's presence is read in the fading of tiny crystals rather than in gas lines alone. A delayed water engine has dynamical consequences. If carbon dioxide dominates early, jets start at larger distances and act over longer arcs, applying torques that evolve the spin state before water wakes. When water finally engages near perihelion, its jets may meet a nucleus already tilted into a new attitude, lighting different terrains than would have been lit if rotation had stayed simple. That mismatch between expected and actual illumination can open stress lines or expose fresh layers unexpectedly, producing outbursts that complicate dust environments and smack into carefully planned windows for spacecraft observations. Hazard is born not from water's vigor alone, but from water arriving late to a body that has been mechanically rearranged by months of other work. There is an even quieter possibility. The bulk water fraction could be low compared to expectations trained on local comets. Formation in a disk region where carbon dioxide condensed efficiently while water remained less abundant would stamp the nucleus with a recipe that seems inverted here but was normal there. Such an origin would not require exotic physics. It would simply say that planetesimal kitchens are varied, and that some cook with more carbon dioxide ice than water ice. That proposition yields the same observational puzzle while reframing it as diversity rather than deviation. Negative detections are not empty. Each upper limit shrinks the space where water can hide. Combine ultraviolet limits on hydroxyl with oxygen line ratios and infrared non-detections, and the remaining corridors narrow to specific depths, surface fractions, and mantle conductivities. Thermophysical models sculpt those corridors into families of permitted interiors. As nights accumulate, the allowed families begin to share features, converging on mantle thicknesses measured in millimeters to centimeters, active fractions measured in a few percent, and crystallization fronts poised just below the depth where seasonal heat will meaningfully arrive. The portrait that emerges is not definite, but it is bounded. Curiously, a late surge of water need not announce itself with a giant tail. Water drives smaller grains more efficiently than carbon dioxide at high temperatures because its flow can be more finely collimated through freshly opened throats. Those grains scatter light strongly, but also leave the nucleus quickly under radiation pressure, thinning the near field even as brightness grows. The result can be a coma that looks only modestly changed while gas production doubles. Careful aperture photometry with varying radii catches the trick by showing that inner regions remain flat, while outer regions brighten as new grains reach them. Activity has shifted, but the eye needs help to admit it. The search therefore becomes a choreography between patience and ambush. Instruments keep their vigil across wavelengths. Models keep their grids ready to absorb new constraints. If water appears tardy but intact, it confirms a layered engine with triggers written in phase changes. If water remains stubbornly faint even near the sun, it argues for an origin where carbon dioxide was king and water a minor courtier. Either answer expands the grammar of small bodies. Either answer alters the expectation of what future visitors may bring. In the practical register, the absence of early water is a relief and a warning. It softens the coma's ion content and reduces some kinds of radio noise. It also raises the odds of sudden changes if structural switches flip near peak heating, changes that can spawn fresh dust sheets and rearrange hazard envelopes on short timescales. Plans that respect both possibilities stay nimble, add cadence to imaging, and watch oxygen lines as closely as anyone watches the bright continuum. The riddle of where the water went is not solved by a single detection. It is solved by the steady refusal to be surprised, by the material's talent for patience. The brightness wanders like a thought half remembered. On some nights, it climbs by a few hundredths of a magnitude. On others, it sinks by as much, and the rhythm refuses to lock. Fresh frames arrive, calibrations tighten, comparison stars hold steady, yet the curve keeps slipping through fingers. The light does not misbehave, it negotiates, trading energy between the hidden nucleus and the restless coma, making patterns that look periodic until a longer stare exposes their drift. Observers begin with the simplest approach: small, circular apertures centered on the moving target, sky annuli set far enough out to avoid the faint tail, and a careful choice of field stars with colors that match the target through the chosen filters. The numbers refuse to flatten. The curve of growth hints that a steady 1/ρ coma cannot be assumed. Subtract such a profile, and residuals ripple. The nucleus is not alone in speaking. Jets write their own letters into the near field, and those letters vary as vents rotate in and out of sunlight. Period searches respond with false confidence. Lomskargel power blooms at several frequencies. Aliases sprout from the daily gaps imposed by Earth's spin, and no single peak holds power across consecutive weeks. Wavelet transforms offer a compromise, showing bursts of coherence that last a few rotations then dissolve. The picture that emerges is not a single spin but a duet, two periods weaving a beat pattern. That is the signature of non-principal axis rotation, a tumbling state where the long axis precesses around the angular momentum vector, while the body spins about the long axis itself. In such a state, the line of sight to any active region changes in a more complicated way than a single rotation can explain, and the light curve becomes a superposition of two motions. Mechanical theory allows the state easily. Small bodies damp energy slowly, when made of porous aggregate rather than monolithic stone. Their interiors behave like foam, with weak contacts that transform shear into heat reluctantly. Outgassing adds energy at irregular intervals, pushing at the figure through jets that rise and fall with illumination and geometry. The Euler equations that govern free rotation accept gentle nudges from those jets, shifting the precession period by minutes from week to week. A nucleus that might have been tidying itself into principal axis rotation finds itself excited, and the light pays the cost in confusion. Amplitude points to shape. In a coma-free light curve, the peak-to-trough swing would be a clean proxy for elongation, yet here the coma dilutes it. Suppose 1/3 of the light comes from the nucleus, and 2/3 from unresolved dust within the aperture. Then a nucleus amplitude of 0.6 magnitude would shrink to 0.2 magnitude in the total. If a jet adds an asymmetric wedge of light on one side of the nucleus, and that wedge turns with the body, the phase of the composite curve will drift away from any simple model tied to silhouette changes. The result is an amplitude that wanders and a phase that slides, two signatures that photometry registers as indecision. Color adds another layer. In nights when the phase angle between sun, object, and observer is small, forward scattering by dust enhances brightness and reddens the slope slightly. As the phase angle grows, that advantage fades. The rate at which it fades becomes a tracer of grain size and texture. A shallow phase curve hints at larger particles, a steeper one at a richer population of fine grains. Polarization supports the story. The negative polarization branch at small phase angles deepens, then reverses, sketching the evolution of dust close to the source. None of these trends settle into a textbook. They tilt, back off, and tilt again, as if the emitter keeps rewriting the distribution of sizes and the roughness of surfaces with each turn beneath the sundae. Occasional spikes trouble the cadence, bright surges lasting tens of minutes to a few hours. Their shape suggests small outbursts, perhaps slabs detaching from a vent rim or pockets of trapped gas finding release through weak crust. The spikes drag along their own dust, altering the coma profile near the nucleus and confusing any attempt to model the steady component. If the spikes repeat near the same rotational phase over several nights, they draw a dotted line around a specific source region. If they repeat at irregular phases, they argue for widespread fragility rather than a single temperamental vent. Photometry crosses into astrometry when jets are strong enough to shift the photocenter. The centroid wanders across the tracking box by fractions of an arcsecond, following the same beat as the brightness. Residuals to the orbital fit breathe-in rhythm, tiny but measurable, a hint that the mechanical language of light and the dynamical language of motion are conversing. If the centroid leads the brightness by a fixed fraction of the beat, the geometry reveals whether the strongest jet lies ahead of or behind the subsolar point on the spinning figure. Models attempt unity. A plausible shape, say a triaxial ellipsoid with modest elongation, spins in non-principal axis fashion while one or two discrete jets emit dust with a cone angle that narrows as insolation climbs toward local noon. The model sums nucleus reflection using a realistic scattering law, coma light using syndines and synchrones, and tail contributions that drift into the aperture as the night goes on. Fit this assembly to the photometry with a Gaussian process that absorbs the slow trends and weight spikes appropriately, and a family of solutions emerges. Each solution explains several nights, then fails on another because a vent choked or a slab fell. The lesson is not frustration. It is the physics of an evolving surface laid bare by light. The practical edge returns. An excited spin state can migrate in period at measurable rates during a single apparition. Minutes per month are not fantasy when jets are strong and the active fraction is small. A shrinking period can push marginal stability toward failure, lifting material at the equator or unseating a ridge where gravity and cohesion are already in a delicate balance. Photometry becomes a seismograph, recording precursors to mechanical change in subtle shifts of amplitude and phase. In a cautious plan, those shifts trigger deeper imaging, longer exposures for coma mapping, and radio looks for gas that might herald an outbreak. Noise refuses to be merely atmospheric. Scintillation introduces correlated errors on short timescales. Moonlight raises the sky and masks small dips, and field rotation in Altaz mounts warps the mapping between coma and aperture. Teams counter with defocus photometry to average over pixel response, with field derotation to keep the coma's orientation stable on the detector, and with multiple apertures to disentangle nucleus, beat from dust drift. When several such streams agree, the remaining variability earns respect. Brightness also keeps score on thermal fatigue. Daily heating and cooling open and close microcracks. Over many cycles, those cracks lengthen, link, and eventually reach the surface, where they open as new vents or close old ones with debris. Each small rearrangement alters the albedo and thermal inertia locally. The next rotation arrives with slightly altered reflectance and a subtly different timetable for sublimation. The change is tiny at any one location, yet the sum across many locations yields the sluggish wandering of the light curve. In that sluggishness lies a map of a world being resurfaced grain by grain. The temptation to force certainty is gently refused. A single period would satisfy the appetite for clean story, but the data argue for layered time. Photometry is patient enough to accept it. Night by night, across sites separated by oceans, the curve is stitched into a tapestry that honors both the nucleus and the coma as co-authors. Where the tapestry thickens, conclusions can be drawn. The spin is not in repose. Jets are not fixed fans. The surface is not a stoic wall. All three wake and sleep on schedules that rarely align for long. Risk hides in surprise, and surprise hides in poor cadence. The answer is to keep watching with care. When the light refuses to settle, it is telling that the engine beneath is negotiating with sunlight in real time. For planners who imagine flybys, and for those who wish to predict dust fields, that refusal is not an inconvenience. It is the most honest signal available. The heartbeat is irregular, but it is a heartbeat. Read correctly. It insists on margins wide enough to include a late surge, on trajectories that avoid the planes where newly launched grains will concentrate, and on schedules flexible enough to respond when a beat slides by a few degrees. In the end, the brightness is a language. It contains nouns for shape, verbs for spin, adjectives for dust, and adverbs for change. It will not settle into a single tense, because the body itself is not stable enough to deserve one. The curve writes motion and weather onto a place that cannot be landed on, and it does so using only the oldest ink, sunlight measured with care. To follow it night after night is to learn a dialect that will be useful the next time a faint traveller writes uncertainty across a dark frame. Speculation arrives as a rumour dressed in circuitry. A small body from another star crosses a familiar sky, and a thought slips in behind the data. Could it be a machine? The question is not a verdict. It is a test of imagination that science must answer with measurements, not mood. The sky accepts no oaths. It accepts only patterns that survive calculation. If the visitor were engineered, its surface might betray design. Specular flashes would speak of flats and edges, of panels that glint like knives in sunlight. A tumbling mirror would carve hard pulses into a light curve, sharp enough to trace angles rather than just areas. Telescopes watch for such glints with cadences that catch minutes and seconds, but the brightness changes rise and fall like weather on a textured surface, not like a square face turned toward a star. Polarization too is consulted, since metallic or dielectric planes can polarize light in ways rough rock and dust rarely manage. The polarization follows the habits of grains, not the discipline of mirrors. Thermal emission carries another signature. An object built to conserve or shed heat has an emissivity pattern that geometry cannot hide. Radiating fins or insulating skins would turn the infrared into a barcode of temperatures. What rises, instead, is a smooth field of warmth traced by distance and phase, gentle where sunlight is gentle, changing as quickly as a small body of low thermal inertia should. No sector glows like a radiator overclocked. No sudden chill marks, a patch designed to keep its secrets behind a vacuum flask. Motion provides the strictest courtroom. If an engine pushes, even with the grace of low thrust, the orbit tells the tale. Gravity writes a script that can be predicted. Photons and expelled gases can annotate the margin, but only within known ranges that depend on temperature and volatile supply. Astrometry of high precision reads those annotations and reduces them to small accelerations along radial, transverse, and normal directions. A sail would favor accelerations that track the solar vector with an airtight loyalty. Jets would favor arcs that flow with local noon and lag into local afternoon. The residuals whisper the comet's language, not a navigator's. No continuous thrust hides in the numbers. Radio quiet is fragile evidence, yet it speaks. Receivers are pointed not for greetings but for accidents. Harmonics of power systems, spurious emissions from switching devices, whispers from a transmitter that did not expect to be in range of curious ears. The spectrum remains a dry field of natural static. Sunlight scatters off plasma and dust and produces a hiss, but it is a hiss without fine imprint. No narrowband spike insists on attention. No drifting tone follows a Doppler story separate from the orbit itself. Listening does not become hearing. A machine need not glow or speak to be a hazard. It could fragment intentionally, or release a cloud of microprobes to sample a star's heliosphere, or test materials against cosmic weather. That thought is met with a practical reply. In the language of mechanics, every fragment is a debt that must be paid at launch. Mass multiplied by speed demands energy. A probe maker would budget tightly, preferring payloads that survive and return information to profligate clouds that dissipate in a foreign sky. The simplest engineer is miserly. Nature is not. Chemistry spends freely when cracks open and sunlit gas finds a path upward. Dust follows the money. The coma seen here spends as chemistry spends. Shape offers another inquiry. A sail works by area, not by mass. High area to mass ratios would allow sunlight to sculpt the path in a way gravity could not cancel. The resulting acceleration would be measurable even at large distances and would grow steeply as the sun brightens. To hide such a sail inside a dusty coma would require a contrivance, equivalent to hiding a kite in a blizzard while insisting the wind does not matter. The photometry and astrometry together are stubborn. They prefer a compact body with a conventional density, not a sheet masquerading as a stone. A message could hide in timing. A beacon might modulate its reflection like a lighthouse coded in minutes and hours, a deliberate rhythm left in the open where any patient observer could decode it. Period searches are conducted with this romantic idea in mind. The curves yield complexity that suits vents and tumbling, not digits and cycles. Nature writes a messy meter. It does not mark a clock. Imagination also entertains shells and scaffolds. Could a thin skin hold volatile pods beneath, opening valves in careful sequence? The emission lines do not comport with ritual. They ebb and flow as illumination changes, and when spikes occur, they look like ruptures rather than commands. The physics of trapped gases and crystallizing ices provides triggers enough to explain every stutter. A sequence that would impress a designer cannot be distinguished from a sequence written by pause and pressure. The discipline of looking does not scold curiosity. It harnesses it. Teams search for techno-signature patterns that could be found even in surprise encounters. A specular glint map that repeats extraterrestrial longitudes. A thermal notch aligned precisely with an artificial tilt. A stream of centimeter-scale objects with identical radar cross-sections. None appears. Instead, there is diversity in grain size, humility in emission, and a warmth that tracks sunlight like any small cold world forced to remember heat for only a short while. There is a different danger bound up in the rumour of machines. Public imagination can multiply a whisper into urgency. Observatories that must plan months in advance can find schedules pulled toward loud uncertainties at the expense of quiet certainties. Attention is a finite resource. The worst case in this register is not an alien contraption. It is a misallocation that starves reliable programs of time because a dazzling thought outshouted the data. The remedy is transparent reporting that quantifies each oddity and a refusal to let poetry outrun probability. Healthy skepticism is not a cage. It is scaffolding around a question. The practice is to pose every mundane test before chasing the miraculous. Run light scattering models that honor the roughness of grains. Map the coma with multiple apertures to isolate the nucleus. Fit non-gravitational terms with realistic jet laws before assigning residual acceleration to thrust. Check radio bands during quiet solar conditions as well as during storms. Place limits on radar cross-section where thermal emission is weakest. This scaffolding does not dismiss wonder. It builds a staircase through it. Suppose that a trace of the unexpected did survive. A glint that repeats at the same subsolar longitude for weeks. A thermal facet that refuses to cool at night. A whisper line on a radio spectrum that refuses to move as rotation requires. The posture would change but slowly. More instruments would be brought to bear. Independent teams would replicate or fail to replicate. Interference would be chased. The confidence that calibrations hold would be assaulted, then rebuilt. If a case for artifice held up under this siege, it would earn its certainty. The sky would support it. Until then, restraint remains a form of respect. Even speculation is educative. Pondering a machine teaches observers where their models are lazy. It exposes assumptions about coma symmetry and about the steadiness of vents. It reveals gaps in cadence where glints might be missed or mistaken for cosmic rays. It prods planners to include high-speed photometry and polarimetry in their toolkits. It leads to radio campaigns that double as lessons in solar wind behavior. The rumor works like a lens, concentrating attention on diagnostics that would be useful regardless of the answer. There is also a softer truth. An interstellar messenger could be both natural and purposeful, not because a builder made it, but because a civilization can use such bodies as couriers without touching them. A window for that purpose would be distant and subtle. A gravitational assist here, a radio watch there. This possibility requires no change to the object itself and does not burden the data with theatrics. It simply invites listeners to keep their ears open while their eyes measure. The passing of a small, cold traveller is an opportunity to test the boundary between physics and myth. The machine hypothesis is not a trespass if it submits to proof. Entertained briefly, it throws the ordinary into relief. Dust behaves like dust. Gas follows energy. Motion respects gravity, unless a vent or photon adds a nudge within known limits. The story becomes cleaner for having been challenged. A rumor is held up to the light and turns transparent. Behind it, the object continues its indifferent journey, and the instruments continue their careful work, having been reminded why the plain languages of temperature, mass, and time remain the most eloquent in the sky. Birthplaces leave fingerprints that survive long journeys. A small body rich in carbon dioxide and slow to yield water suggests a nursery where ice learned a different hierarchy. That nursery could be colder, more strongly irradiated, more dynamically restless, or made from a mixture whose balance of carbon and oxygen tilted chemistry toward a different equilibrium. Each possibility grows from known physics. Each draws a map that reaches back to a time when grains were not yet stones, and rings in a young disk were factories rather than ornaments. In a protostellar disk, temperature falls outward like a patient gradient. The water snowline sits close to the young star where the midplane first cools enough for H2O to freeze. Farther out lies the carbon dioxide snowline, where CO2 condenses as frost on grains. Beyond that, still colder, waits the carbon monoxide snowline. These boundaries are not sharp. They breathe with accretion heat, with stellar flares, and with the slow settling of dust that changes how starlight warms the midplane. Where a snowline lingers, solids grow rapidly. Gas pressures pile up. Pebbles drift inward under drag, then stall at pressure bumps and assemble into planetesimals. A body born at the CO2 snowline would inherit abundant carbon dioxide ice baked into its pores, while water ice would be present but organized differently in texture and depth. That blueprint alone could explain a coma, where CO2 takes the lead when sunlight arrives. Radiation alters the script before stones congeal. In crowded star-forming regions, ultraviolet light from massive neighbors floods young disks. On grain surfaces, UV breaks water into OH and hydrogen, and breaks CO into carbon and oxygen. OH radicals find CO with enthusiasm and assemble CO₂-rich a quiet chemistry lab made of ice and dust. The result is a mantle enriched in carbon dioxide relative to water, especially in layers exposed to photolysis. A planetesimal that aggregates these mantled grains locks CO2 into its near surface. Later, when a star's light warms the exterior, those layers wake earlier than deeper water ice, and the escaping gas looks like a decision rather than a coincidence. Metallicity shapes the nursery as well. Fewer heavy elements mean fewer solids per unit gas, lower opacity, and a disk that cools efficiently. Snowlines in such a disk rest closer to the star and are steeper in their thermal gradients. Closer snowlines concentrate pebbles in tighter rings and shorten the migration path of drifting grains before they stall. In that regimen, a planetesimal can form in a region where carbon dioxide is stabilized, while water ice remains trapped beneath sintered crusts built from rapid cycles of warm and cold. Metal-poor environments may also have lower initial budgets of short-lived radionuclides that heat small bodies from within. With weak internal furnaces, amorphous ice and clathrate cages survive for eons rather than annealing early. The body carries forward a delicate structure that biases which gases find paths to the surface. Another imprint comes from the ratio of carbon to oxygen in the gas. Disks inherit this ratio from their parent clouds and modify it as ice traps oxygen into water beyond the water snowline. Gas closer to the star can become carbon-rich as oxygen freezes out. Solids farther out become oxygen-rich as they collect water and CO2. A world assembled near the boundary where gas and solids exchange dominance can end up with a layered volatile pantry, rich in CO2 at modest depths and with water relegated deeper. If later heating is mild and episodic, Colorado 2 takes the role of herald, announcing activity long before water discovers a way to breathe. Structure forms where rings and gaps appear. Observations of young disks show concentric bands carved by pressure bumps and by planets still gathering mass. These ridges act as conveyor belts and storage bins for icy pebbles. Near the CO2 line, pebbles may drift in from colder regions, carrying CO2 frost, and then shed that frost like snow as they cross into warmer gas. The shed frost can recondense onto resident grains just outside the line, enriching a narrow annulus. Collisions inside that annulus, helped by turbulence and by streaming instabilities, birth planetesimals whose shallow layers are saturated in carbon dioxide ice. In time, those bodies become projectiles in the grand billiards of planet formation. Some are scattered inward, some collide and shatter, some are ejected entirely, trading a star for the dark between stars. Ejection mechanisms leave their own nuance. A giant planet that grows rapidly near the CO2 line can hurl planetesimals outward through resonances and close encounters. A migrating planet that crosses the line can scoop up pebble streams and seed a storm of interactions that sends debris into the heights of the system. A binary companion can tilt and stir reservoirs through long-period exchanges of angular momentum, handing small bodies to gravity slingshots that end in escape. In each case, an object leaves early enough that its near-surface chemistry remains largely unprocessed by long summers. It enters interstellar space with mantles intact, pores still clogged or open in patterns set by the nursery, rather than by a late life of repeated perihelion passes. Age decides how much of that nursery survives. If ejection happens while the host star is still young, the object travels for billions of years through diffuse clouds and quiet plasma. Cosmic rays thread its outer centimeters, darkening organics and strengthening a crust. Deep within, low conductivity insulates original textures. If ejection happens late, after a few or many passages near the host star, then near-surface layers are already reorganized by thermal cycles, yet deeper deposits remain faithful to formation. The present behavior would distinguish these cases. An early ejection favors an engine that starts with CO2 at low temperatures and keeps water dormant behind an unbroken rind. A late ejection favors mixed seasons and scars that act as ready-made vents. The coma would broadcast which past occurred through the way activity wakes and the size distribution of the grains it lofts. There is a harsher nursery still, one not defined only by temperature but by violence. In a massive cluster, supernovae enrich and disturb the neighborhood. Shock waves sweep through clouds, seeding radionuclides in pulses that may or may not reach a given disk. If the pulse is weak, the inventory of heat makers like aluminum-26 is low. Internal melting is suppressed. Clathrate cages survive. CO2 trapped in cages rides deep into time without release. When such a body finally meets a new star, those cages open only when local heating crosses thresholds that depend on pressure and geometry. The pattern of gas that emerges is punctuated, like a score written with rests as important as notes. Conversely, a disk around an active M-dwarf lives under a flickering lamp. Flares drench the inner and middle regions in UV and X-rays with eccentric timing. Photoevaporation eats at the disk from above, skimming gas and altering pressure profiles that shepherd pebbles. Snowlines migrate in sawtooth paths rather than smooth arcs. In such an environment, planetesimals can inherit layered skins where CO2 produced by photochemistry sits atop water that never fully reorganized. Later, as stars age and calm, the memory of those early flashes remains encoded in the sequence of which gases wake when. Even the architecture of solids matters. Pebble accretion builds bodies from centimeter-scale, ice-rich balls that drift and settle. The porosity of a pebble pile is high and anisotropic. Channels form along contacts, where pebbles pick up weight and deform. These channels make directional plumbing that favors certain longitudes when the sun finally arrives. If CO2 coats pebbles and water cements them deeper, the first thaw sends CO2 along those paths like scouts. Water lags and presses against thicker obstacles. Outgussing patterns that seem capricious at astronomical scales become inevitable at the scale of microstructure. Origin is therefore not a single dot on a map, but a family of conditions. Temperature gradient, ultraviolet field, dust content, planetary architecture, and cluster history together write the recipe. Change any one term, and the resulting world expresses a different ratio, a different permeability, a different strength. With that understanding, a comet rich in carbon dioxide need not feel like an outlier. It is a representative from a different workshop, one where the CO2 snowline was productive, where UV chemistry worked loudly, or where internal heat never erased the earliest arrangements of ice and pore. This perspective has practical worth. If such nurseries are common, interstellar visitors will often carry early waking volatiles that sculpt long, gentle comae far from any star. Dust fans built by those gases will be dominated by larger grains that remain near their path and persist for weeks. Spacecraft pathfinders that hope to sample these travelers should plan not for a single near-perihelion sprint, but for early campaigns that map dust sheets formed far out. The timing of hazard and the flavors of opportunity follow from birth as much as from present sunlight. There is a grace in recognizing that a stranger's behavior is faithful to a home not seen. The small decisions made by a cold disk, by the way it handled light and pressure during the first million years, echo across distances that mock scale. When a faint tail brightens and a gas band writes its line into a spectrum, the echo arrives. Listening to it with patience turns a passing spark into a postcard from a harsher nursery that still speaks through the way its child breathes. Word count 1182, awaiting un. Radiation works slowly, with the patience of frost writing lace on glass. Far from any star, the only weather is made of particles and photons that arrive from every direction. Cosmic rays punch through ice with the energy of protons accelerated by forgotten shocks. Ultraviolet light threads gaps that are unshielded by a planet's air. Measured in years, the work looks like nothing. Measured in millions of years, the work adds up to a crust, to chemistry that is no one's first guess, to a surface that answers heat differently than the bulk beneath it. A cosmic ray turns a track of ice into a brief laboratory. It breaks water into hydrogen and oxygen and leaves radicals stranded where bonds used to be. It scrambles carbon-bearing ices, nudging carbon monoxide toward carbon dioxide, building organics molecule by molecule like a slow maker of varnish. Every passage lowers albedo a little, because complex organics absorb light greedily. Every passage toughens the topmost layer a little, because those organics glue grains together and resist the first breath of sublimation. After deep time, the result is a rind a few millimeters to centimeters thick, dark, cohesive, porous in a selective way, and stingy with water. Ultraviolet finishes what cosmic rays begin. Photons that carry just enough energy to rearrange, but not enough to destroy accumulate effects with a miser's discipline. Photolysis of water leaves trapped oxygen and peroxides in tiny cavities. Photolysis of carbon monoxide and carbon dioxide shifts the mixture toward a spectrum of carbon chains and rings that bind dust like mortar. The net effect is paradoxical. The surface grows darker, and so it absorbs more sunlight. Yet it also becomes a better insulator, as pores close selectively and heat conduction falls. The very layer that warms most readily also hides the colder interior from that warmth. Micrometeoroids bring a different tool. Grain-sized impacts at high-speed loft dust in small fountains and fuse fine materials into glassy coatings. The topmost centimeter becomes a garden zone, where microshocks shuffle grains and sift fines into hollows. Ice retreats from this zone because every impact cuts new surface area, and any exposed ice that cannot outrun the next impact sublimates and leaves dust behind. A lag deposit forms, a blanket of refractory material that keeps the cold below safe. That blanket does not seal like a lid. It filters, and filtration has preferences. Permeability is the quiet heart of what radiation builds. Pores shrink and kinks in channels rise where organics settle, and those kinks are more forgiving to smaller molecules than to larger ones. Carbon dioxide molecules are smaller than water clusters and travel more easily through a maze choked by organic films. In freeze-up conditions, migrating CO2 can plate frost in shaded pores and later, under gentle warming, ride those paths outward. Water vapor, with its stronger tendency to stick to surfaces and form clusters, becomes the prisoner more often than the passenger. The coma reports this bias as if a decision had been taken, when it is only a material consequence. Amorphous ice deep below remembers another part of the story. Radiation damages its structure and stores potential energy in its disorder. The passage from amorphous to crystalline releases that energy as heat and frees gases held in cages. If the crust above was thickened by radiolysis, the heat travels upward more slowly, and the release occurs later and in pulses. Under those conditions, a pocket can become a pressure vessel for a while. When a crack finally connects pocket to sky, the outflow is abrupt, and fragments of darkened crust are carried into space. The fragments become seeds for temporary swarms that follow the path briefly before dispersing, and the surface is left scarred with a fresh vent whose margins are still lined with radiation-baked organics. Laboratory studies of icy mixtures show that oxygen formed by radiolysis can accumulate as O2-inch traps, especially where porosity allows diffusion but bars escape. Add hydrogen also created by radiolysis, and a fraction recombines to water, but not all of it does so promptly. Warms slowly, and trapped gases build pressure against the crust. The mechanical threshold for a small fracture is low in aggregates held by van der Waals forces and syntonechs, and the moment that threshold is crossed depends on where the crust is weakest, not on where the heat is strongest. That mismatch is why outbursts can come from shadowed walls and from rims of old pits, places chosen by structure rather than by sunlight. Optical properties evolve under radiation too. A fresh surface reflects a color that hints at ices and silicates. A seasoned surface reflects a deeper red characteristic of complex organics. With still more dose, the slope can flatten again as carbonization proceeds and scattering becomes dominated by roughness rather than by molecular features. If a crack opens and exposes virgin material, photometry catches a small bluing in the inner coma, a brief flash of youth in the color before solar light and particle rain tan, the grain's mid-flight. That flash is a diagnostic with teeth, because it dates the exposure and turns color into chronology. Mechanical properties do not stay constant. Radiation compacts near-surface ice very slightly and embrittles organics. The result is a skin that resists low stresses until it does not, a skin that fails suddenly rather than deforming slowly. Below it, the material remains more compliant. Temperature cycles add their own fatigue, opening and closing microcracks at the diurnal cadence. The combination is cruel, but predictable. Crack tips sharpen under thermal stress, radiation cements lips near the surface, and when a pathway forms, it does so like a zipper. The opening propagates in a line, lifting a sheet that then shatters. The shards inherit the dark coating and present a larger surface to light, so they heat and sublimate faster than the intact terrain they left. The coma records a short-lived enrichment in coarse grains that appears, confuses photometry for a night, then fades. Radiation also writes on the electrical life of a surface. Photoelectrons escape under solar UV, leaving positive charge that migrates along the top layer. In shadow, secondary electrons generated by cosmic rays add negative charge with a different rhythm. Across dawn and dusk lines, small electric fields lift the finest grains and redeposit them in places where fields cancel. The dust bookkeeping set by gravity and gas is then edited by electrostatics. Over long time, this process can sort particle sizes across slopes and ledges, producing patches that are slick for gas and patches that are stubborn. That sorting becomes a local control on which vents switch on when the sun swings into a new hour of rotation. The long itinerary between stars grants more than dose. It grants time for volatile migration even in the deep cold, because sublimation need not be vigorous to be effective when millions of years are available. CO2 molecules that strike a wall do not always stick. If they hop and find a path, they drift downhill in temperature and pressure toward voids nearer the surface. Over epochs, a gentle distillation occurs, enriching the upper tens of centimeters in CO2 while depleting deeper stores and leaving behind a matrix more strongly dominated by water and dust. Then, when a bright star appears ahead and distance falls, the first gas available is the gas that the journey has already shepherded into position. What has been made by radiation has consequences for hazard and for opportunity. A crust that is strong enough to hold until it fails will time its failures unpredictably on human schedules. Small outbursts that lift coarse debris can add navigation challenges where none were expected, not just near peak heating but at odd heliocentric distances where a model that ignored radiolysis would predict calm. Conversely, a surface enriched in complex organics delivers spectral signatures that teach chemistry when the right instruments watch at the right wavelengths. The darkening of grains improves thermal contrast and aids thermal imaging in tracing relief. The very processes that increase operational risk also sharpen the tools that can read a world's history. The paradox remains that radiation both hides and reveals. It hides water beneath varnish and altered pores. It hides hot spots behind an insulating blanket. It hides vent geometry until failure chooses to speak. It reveals origins by writing colors that betray photochemistry. It reveals time by the thickness of a mantle. It reveals pathways of gas through subtle biases in what escapes first. To understand a small body that has drifted under this patient hand is to accept that surface and interior are in different centuries. The top remembers long winters of charged particles. The interior remembers a young disk. Sunlight negotiates between them. No one needs romantic language to see that time is the main artisan here. A traveller that left its first home as a cold shard has been engraved by a field of invisible carpenters. Their chisels are protons, electrons, photons, and silica needles moving too fast to be seen. Their workshop is the dark. Their method is repetition without complaint. When the shard enters a warm room and begins to breathe, it breathes through that engraving. Every hiss of gas and every drifting fleck of dust carries a record of the slow work done far from any Sunday. Reading it well is the difference between an object that surprises and a world that confesses. Brittle ice does not crack like glass. It negotiates failure through pores, veins, and buried seams. Stresses accumulate from three quiet causes: uneven heating across pits and capes, rotation that drifts toward faster beats under jet torques, and internal pressure where gases gather behind crust. None alone must be dramatic. Together they find the weak path, and the weak path does not stop until a panel lifts. What leaves the surface is rarely a powder. It is a plate that shatters as it enters sunlight and vacuum, a family of fragments from sand grains to fist-sized shards. Three fragmentation modes dominate. Thermal spallation peels thin sheets from sunward cliffs when daily temperature swings open millimeter-deep cracks. Overpressure rupture blows out a cap when migrating gas fills a pocket beneath a rind, strengthened by radiation chemistry. Rotational shedding loosens equatorial ridges when centripetal demand finally outruns cohesion. Each mode launches debris with characteristic speeds. Thermal flakes drift off at a few meters per second. Overpressure adds tens of meters per second for the smallest pieces. Rotational loss lets blocks barely clear escape, then disassemble into trains of rubble that trail the parent along its path. The fragments inherit the parent's velocity through space, plus the small push that pried them free. Against that enormous baseline, a meter per second is a footnote, yet that footnote decides how the cloud spreads. Grains the size of cigarette ash take the hint from sunlight quickly. Radiation pressure reduces the sun's pull on them and bends them into graceful arcs that veer from the parent line. Pebbles and cobbles feel the light only weakly, so they remain loyal to the original trajectory and form a dusty ribbon that can persist for weeks. The physics is simple: an effective gravity that is smaller for smaller grains, an initial squirt that is larger for lighter shards, and a star that is patient. A debris cloud carries a census written as a power law. For every large piece, there are many small ones, with a slope steep enough that the total surface area is owned by the finest dust, while the total mass lives in the largest survivors. The eye responds to area. Instruments see the cloud as a soft brightening and a thickened tail. Hardware responds to mass. A millimeter grain at cosmic speed is a kinetic hammer. Consider a sphere 1 millimeter wide with icy density. Its mass is about 5 times 10 to the minus 7 kilograms. At 30 kilometers per second, the energy is roughly 230 joules. the sting of a small firearm focused into a spot smaller than a pencil eraser. Solar array's chip, radiator's scar, a window's coating turns to glitter. The smallest grains deliver different trouble. Microgram particles vaporize on impact and make expanding plasma plumes that confuse star trackers with momentary constellations that do not exist. Thermal control faces local hotspots where a flurry of micro-impacts deposit heat faster than the surface can sink it. Telemetry spikes as charged plumes interact with electric fields around booms and antennas. None of this threatens a spacecraft's life on its own. It threatens the mission's confidence at exactly the hours when attention must be on engines and pointing. Dust dynamics turn a local accident into a regional concern. Where the parent's path crosses the ecliptic plane, a fragment ribbon folds into the same plane and piles up by perspective. The pile is thin along the normal direction, fat along the orbital direction, and almost invisible unless a telescope stares along the sheet. Once recognized, it becomes a line in space that other travelers must not cross casually. This line drifts with the parent, stretches as radiation sorts grain sizes, and frays into filaments when small outbursts punctuate the release. A probe that must pass near the line can do so safely if it meets the sheet at a steep angle and at a time chosen to avoid the densest lobe. Caution is geometry, not panic. A harsher branch of the story is rare but instructive. If a block breaks while still bound to the nucleus by a slow relative speed, it can linger near the body for hours to days, circling loosely as sunlight works on its corners. Each circuit changes the block's attitude to the sun and opens different pores. Miniature jets puff, alter the block's spin, and eventually set it free. The wake near the parent becomes an archipelago of temporary companions, visible only as a slight broadening of the central condensation and a rise in polarized light at certain angles. To approach through such an archipelago is to navigate through a field of moving, uncooperative targets that do not announce themselves until they flash or strike. Fragmentation has signatures that observers can recognize quickly. Surface brightness profiles steepen near the nucleus as fresh, coarse grains fail to fill the outer coma with fine haze. Polarization increases at intermediate phase angles and rotates its plane in patterns that simple jet models cannot reproduce. The tail's position angle jitters by a few degrees from night to night as large pieces tug the photometric center off the instantaneous antisolar line. When such signs appear together, hazard maps are updated. The safe corridor swings wider. Cadence rises. Telescopes trade some spectral ambitions for deep imaging that extends the faintest isophotes. In the logic of safety, wings of light are alarms. Operationally, the first defense is distance. Whipple shields and stuffed blankets defeat hypervelocity grains up to a design threshold, but optics and booms cannot hide behind armor. The difference between a 300-kilometer miss and a 1,000-kilometer miss is not a marginal comfort. It is a 100-fold reduction in particle flux for power law-size distributions that assign more grains to the neighborhoods closest to the parent line. The second defense is timing. Wait for the outburst plume to relax, then cross. The third is orientation. Present robust faces to the expected flux. Point instruments away during transit. Star trackers can be switched to guarded modes that accept fewer stars and ignore flashes that last only milliseconds. The nightmare vision of a planet-crossing meteoroid stream born from a hyperbolic visitor has a certain cinematic pull. The probabilities work against it. To seed a stream that Earth would meet, a release must occur near the node where the visitor's path intersects the planet's orbit, and it must occur with enough mass and the right spread in grain sizes that the cloud persists until the encounter. Even then, the hyperbolic geometry gives the stream a high relative speed and a short window. Meteor radars could see a brief rain of very fast traces. Satellites could feel a thin tick of extra micrometeoroid hits. The display would be a postcard, not a chapter. Closer to the parent line, the concerns are more immediate. A deep space relay stationed near a Lagrange point, a Mars orbiter en route along a transfer arc, a solar observatory cruising high above the ecliptic. Each can find its risk budget tilted by a fragment event that no schedule predicted. Long mission lives mean long exposure to coincidence. The antidote is a standing habit of sky awareness. Survey images that catch a new plume trigger notices. Ephemerides for the hazard sheet are posted. Narrow time windows are flagged as do not cross. In this register, the worst case is missing the memo. Electrostatics and plasma add nuance to fragment clouds. Fresh surfaces charge differently than seasoned grains. Sunlit shards shed photoelectrons and arc slightly as they pass into shadow behind the nucleus or into regions where the magnetic field rotates. The smallest grains can be picked up by the solar wind and steered along field lines into filaments that peel off the main dust ribbon. That peeling is beautiful and dangerous. It delivers small particles far from the obvious tail into volumes a cautious planner might otherwise have declared clean. Conservative maps grow a margin around the parent path to account for such filigree. Numbers guide prudence. A flux of 1 mm grains as low as 1 per square kilometre per hour becomes mission-shaping if a vehicle must cross the sheet at tens of kilometres per second with unshielded apertures. The rate can be much smaller and still matter for delicate surfaces. For microgram grains, a modest fluence over minutes can fog a camera with persistent glints. There is no virtue in toughing it out if a delay of hours or a change of a few degrees in crossing angle reduces flux by an order of magnitude. Space routinely rewards patience more than bravado. Fragmentation is not only risk, it is also revelation. Breaks expose interiors that have not seen sunlight since assembly. Spectra of fresh shards tell of ices and minerals before veneers altered them. Polarimetry of newly minted grains writes a clearer story about texture and porosity than old dust does. Radar echoes from large fragments yield sizes and densities that a coma could not betray on its own. The same event that complicates navigation becomes a gift to understanding when watched from a distance with the right instruments ready. The honest worst case is modest in scale and sharp in consequence. A plate lifts, shatters, and populates a narrow sheet with grains from microns to millimeters. The sheet grazes a path that a spacecraft had planned to cross on a schedule that seemed conservative only days before. The crossing happens. A few grains strike optics and star trackers. Guidance falters for seconds. A radiator panel blooms with pockmarks that degrade heat rejection by a percent here, a percent there. None of it ends a mission. All of it tightens margins. The lesson is immediate. Keep maps current, keep distances respectful, and treat a faint rise in the inner coma's brightness slope as more than a curiosity. The sky judges plans by physics, not by confidence. A brittle body that sheds grains writes a temporary lane through space that cannot be ignored. Reading that lane correctly, and choosing to cross it well or not at all, shrinks drama into good practice. The shards drift on, the ribbon thins, and the hazard ebbs with time. What remains for those who watched is a sharper picture of how fragile ice fails, and how that failure writes itself into the mechanics of dust. In that picture, caution and knowledge share the same frame. Gravity writes the main sentence, yet smaller authors annotate the margin. The annotations arrive as forces without hands, the quiet pushes of sunlight and the breath of escaping gas. They do not change the grammar of a hyperbola, but they shift commas and clauses enough that careful readers can see the edits. The work of this reading is astrometry that refuses romance, measurements of dots against a grid that show whether physics beyond the inverse square law is having its say. Begin with the simplest push. Gas leaves the surface at hundreds of meters per second and carries momentum with it. Thrust equals mass flow multiplied by exhaust speed. If vents release 1/10 of a kilogram each second and the flow leaves at 300 meters per second, the thrust is 30 newtons. A nucleus only a kilometer across with cometary density has a mass near a few times 10 to the 11th kilograms. The resulting acceleration is a few times 10 to the minus 10 meters per second squared. Sustained for months, that becomes a delta V measured in millimeters per second to centimeters per second. which is small for a traveler moving tens of kilometers per second, yet large enough to move predicted positions by tens to hundreds of kilometers if ignored. Direction matters more than magnitude. Modelers describe three components: radial points inward or outward from the sunday, transverse follows the motion along the path, normal lifts above or drops below the orbital plane. The same thrust can raise or lower closest approach distance depending on how those components combine. Sublimation rarely points perfectly anti-solar. Vents live on slopes, the body rotates, and the diurnal lag between heating and response leans the flow into late afternoon directions. That skew plants a transverse term that subtly advances or delays the object along its path. The normal component, usually smallest, tilts the plane by tiny angles that make their presence known over many weeks. The time dependence of the push is folded into a scaling law that rises near the sun and fades far out. For water-dominated activity, a traditional choice peaks sharply near the inner system. For carbon dioxide, the onset is earlier and the tail of the function is longer. Choosing the wrong scaling law is not a technicality. It misallocates thrust to the wrong distances and grows a prediction that will drift away from what telescopes will later measure. A sober fit lets data choose which law the object prefers, and it tests whether a mixed law improves the story, because more than one volatile can make its voice heard across different arcs of the journey. Light pushes directly, though faintly, on the solid body as well. Solar radiation pressure at 1 astronomical unit amounts to a few micronewtons per square meter. A small object with a cross-section of 1,000,000 square meters feels a handful of newtons. Divided by the mass quoted above, that yields an acceleration 2 orders of magnitude smaller than typical gas thrust in active phases. It is not nothing, but it is a second violin that rarely leads. On dusk grains it dominates. On the nucleus it usually stands behind the curtain. Torque is the companion to thrust. A force applied off, center changes spin. For a jet acting at a lever arm of a few hundred meters, 30 newtons become a torque of order 10 to the 4th Newton meters. The moment of inertia for a porous ice and dust sphere a kilometer wide is on the order of 10 to the 16 kilogram meter squared. The change in angular velocity accumulates slowly at first, then faster if the same vents keep the same hours. Weeks of coherent torque shrink a rotation period by minutes, and a change of minutes can move sunlit zones enough to redirect which pits wake and which go to sleep. The rotation can process into a tumbling state if torques are not balanced. The sky will not announce this with fanfare. Photometry will, when amplitudes wander and phases slide in step with the changing body language of the nucleus. Orbit determination folds all of this into a patient loop. Fit a gravitational solution to a growing arc of positions. Plot observed minus computed residuals on the sky. If they scatter like fair noise, leave the model alone. If they bend, as if a hand were on the path, offer the model the 3 non-gravitational components multiplied by a scaling law and ask whether the residuals relax. A Bayesian sampler is often used because uncertainties flow through parameters in ways that least squares can understate when comae swell and centroids wander. The sampler breathes across a family of solutions and reports not a single answer, but a cloud in parameter space where confidence lives. Small biases creep in where light departs from a point and becomes a fog. Astrometry from a coma must choose a center that may not be the nucleus. If the inner cloud is brighter on one side, because a jet opens there, the chosen center creeps toward that side. The shift can be a fraction of an arcsecond, which sounds small until it is repeated night after night in the same direction. The remedy is to model the inner coma and subtract it, to use small apertures that privilege the unresolved core, to deconvolve when seeing permits, and to inflate uncertainties honestly when weather or geometry do not. The improvement shows quickly when residuals lose their drift and relax into symmetry. There is an upper bound that comfortingly refuses to be broken. No reasonable non-gravitational fit, even one that assigns generous thrust to every day near peak activity, can turn an interstellar curve into a path that strikes a planet by surprise. The total impulse available is too small, the direction too variable, the leverage too brief. The danger is not impact. It is the slow migration of where the dust will be dense and when a spacecraft might unluckily meet it. Along track shifts of a few hundred kilometers slide dust sheets across planned corridors. Cross-track shifts of similar scale move narrow filaments above or below a safe lane. In that register, a small acceleration that survives the fit is a practical alert. Occasionally the sky is generous and adds a constraint from radar. A single echo at the right geometry pins range and range rate to precisions that optical astrometry cannot achieve. Phase delay and Doppler width speak to size and spin as well. Most interstellar visitors are too faint and too far for such luxuries. The field makes do with light and patience, and inserts radar priors only when they exist. The habit of not pretending they exist when they do not is part of the culture that keeps predictions honest. Uncertainties are communicated not as a number but as a corridor. The central line is an ephemeris. Around it sits a swath that shades where the object could be when propagated to a given date. The swath tightens with each good night and loosens when weather steals cadence. Non-gravitational parameters, once accepted, shrink the swath more than continued denial would, because the model no longer must explain systematic drifts as random noise. The corridor is the language mission planners understand. It tells them not only where to point, but how much margin to keep when a trajectory threads between brightness and safety. A different class of subtle push waits in sunlight itself. Uneven reflection and thermal re-emission can alter spin over long times, an effect analogous to what asteroids experience. On a small active nucleus, the breathing of gas drowns that whisper. But once activity subsides, the whisper remains and works over years to align, slow, or speed rotation in ways that are more easily predicted than jet talks. It is a future term, not a present one. Yet it enters the narrative because non-gravitational influences form a spectrum from impulsive to secular, and the full picture obeys them all in their allotted times. It is tempting to ask for a single worst push. Nature refuses to provide it. A strong jet near perihelion gives the largest instantaneous acceleration, but its direction wobbles as the body turns. An earlier, weaker jet contributes for longer, and so accumulates a similar impulse in gentler fashion. A skewed coma that biases centroids creates a ghost acceleration, if not corrected, and that ghost can be larger than a real one for a while, until corrections catch up. The discipline is to treat every suspicious residual as a witness, not a verdict, and to let multiple witnesses establish a story. Conservatism has signatures in the planning room. Predictions are made with and without non-gravitational terms to bracket outcomes. Dust hazard maps are drawn for both bracketing paths. Schedules hold maneuver options that can shift a crossing by hours to move from a denser ribbon to a thinner one if late data recommend it. Instruments practice safe modes that conserve while pointing away from expected flux, then wake quickly when clear. In this choreography, the smallest forces earn respect not because they are powerful, but because they are cumulative and because they hide inside measurements that look ordinary until time reveals their pattern. The last word belongs to the dots on the sky. Each is a handshake between photons and a detector, between a beach of silver or a sea of silicon and a point of light that left its source hours ago. Stack enough handshakes and a path appears. Compare path to prediction and a small remainder stays. Inside that remainder live the non-gravitational nudges. They are not ghosts. They are the breath of an ice machine and the soft shove of sunlight on matter. Measured well, they tame uncertainty without pretending to banish it. Measured poorly, they grow into avoidable surprises. A calendar begins with geometry, not with days. Draw the hyperbola in a heliocentric frame. Mark the two nodes where the path cuts the ecliptic plane. Shade arcs where sunlight rises enough to wake the volatile layers that act first, then darker bands where heating could push a fragile surface toward failure. Around each mark, widen or tighten the band according to uncertainty in non-gravitational forces. This becomes a schedule of encounters, not appointments with planets, but windows when dust, gas, and plasma are most likely to matter for instruments and spacecraft. On the inbound leg, the first window opens while the visitor still sits far from the Sunday. Carbon dioxide can begin to flow at distances where water remains quiet, so the earliest activity is faint and long-ranged. That combination writes a broad, low-contrast dust fan, whose outer wings matter more than the bright core. The hazard here is subtle. Millimeter and sub-millimeter grains, once lofted, linger close to the trajectory for weeks. Any spacecraft scheduled to cross the projected path within a few 100,000 kilometers during this phase should do so steeply rather than skimming along it, because a steep crossing reduces time spent inside the wings that a shallow crossing would sample for far longer. The inbound node creates the next entry. Where the path intersects the ecliptic, a sheet of dust released over many rotations lies nearly in the same plane as most interplanetary traffic. Projection squeezes this sheet into a sharper filament called an antitail when the line of sight grazes the plane. For operations, the word filament should ring louder than the word tail. The highest particle concentrations lie near that narrow sheet. Crossing it obliquely, preferably at tens of degrees rather than a few, trims flux by an order of magnitude even if total mass loss is unchanged. The best crossing time is soon after the node, before the sheet thickens with grains that require less radiation pressure to deviate. Weeks around perihelion are reserved for contingency. Peak heating can align with structural thresholds. A thin rind strengthened by radiation may hold just long enough to fail in a brief outburst. The calendar therefore sets aside a guard band that begins well before closest solar approach and extends well after it. Within this band, imagery cadence is increased. Photometry is watched for rising amplitudes that hint at spin changes, and spectra are checked for compositional switches that often accompany new vents. Deep space assets are encouraged to treat days inside this guard band as caution hours, rotating sensitive surfaces away when passing near the projected tail and sharpening dust models daily to update the three-dimensional shape of hazard zones. Earth receives a separate line in the schedule, even when distances are comfortable. For ground and Earth orbit operations, two alignments matter more than proximity. If the plasma tail passes close to the Earth-Sunday line, long wavelength radio links that skim the heliosphere can experience scintillation. If the dust sheet aligns such that the antitail lies near Earth's orbital plane, very small particles can enhance the background micrometeoroid flux briefly. Neither event threatens infrastructure in any realistic scenario, but both can degrade data and require coordination. The calendar marks such alignments to advise radio networks and to alert meteoroid monitors to expect a short surge of very fast, faint traces that would otherwise look like noise. Post-perihelion, the calendar does not end. Dust released near peak heating continues to stretch into a drapery along the path. Larger grains cling to the trajectory, forming a ribbon that thins as it lengthens. The risk here is time-shifted. A spacecraft that seemed safe during the main event can meet the lingering sheet many weeks later, far from the place where the parent seemed most active. This delayed crossing is mitigated by simple geometry. Adjust the encounter to cut the ribbon at a right angle, or slide the date a few days so that the denser lobe has drifted. In many cases, a small change in timing buys a large change in safety. A calendar also carries opportunities. Spectroscopy of faint gas bands benefits from nights when the phase angle is moderate and the dust contribution is minimized in chosen apertures. Polarimetry prefers times when the phase curve crosses a known turnover, allowing grain properties to be extracted cleanly. High-resolution imaging of jet morphology excels when the line of sight is not tangled with the orbital plane, because projection can otherwise exaggerate or hide structures. These scientific windows sit beside operational cautions without conflict. The same planning that avoids dust can favor clean views of chemistry and structure. For mission planners, the calendar converts models into thresholds. A change in the brightness slope within a fixed inner aperture implies that larger grains have entered or exited that region. If the slope steepens beyond a preset value, delay a crossing. A rise in the oxygen-line ratio that indicates an increasing contribution from carbon dioxide tells of earlier onset at greater distances. Widen the early guard band, if this trend holds. A measured drift in rotation period above a set rate flags increasing torque. Treat subsequent days as more likely to host minor outbursts. These triggers are designed before operations begin, and they are tied to decisions that require no debate when the numbers cross them. Different neighborhoods need different marks on the calendar. For solar probes traveling inside the orbit of Mercury, the plasma tail is a navigation nuisance more than a particulate hazard. But the coma's ion chemistry can complicate in situ instruments that sample the solar wind. For observatories near Earth Sunday L1 or L2, the line of sight through dust can add faint glints that star trackers must ignore. For planetary missions en route across the inner system, the dust ribbon is the only feature that drives rerouting. Each class of asset inherits a custom subset of the windows, and each subset follows the same logic. Geometry first, threshold second, margins throughout. Uncertainties are treated explicitly. The calendar does not present a single date for any window, but a shaded interval that captures how non-gravitational parameters and activity models could stretch or shrink it. As new astrometry and photometry arrive, the shaded intervals are redrawn. In practice, this looks like a moving corridor on a planning chart. The corridor narrows with every clean night, and decisions that were deferred until the last responsible moment can be taken with more confidence. When cadence is lost to weather or scheduling, the corridor widens. The plan assumes the wider shape rather than pretending a precision it does not own. Fear loves absolutes. A calendar refuses them. It replaces yes or no with when and how long. It locates the brief hours when an antitail is a razor in the sky and distinguishes them from the many more hours when it is a rumour. It isolates the days when an outburst would cause the greatest nuisance and separates them from the long slope of safe passage. It sets expectations for communications, for instrument modes, for pointing strategies, for data quality flags. It makes clear that worst case in this context is not a catastrophe, but a preventable inconvenience if timing and angles are respected. There is a quiet moral buried in the schedule. The same care that protects hardware also amplifies knowledge. Telescopes that pivot to avoid dust during a crossing take time to map the dust instead, and those maps reveal the physics of emission and grain growth. Radio networks that expect scintillation arrange simultaneous multi-frequency measurements, and those measurements expose the plasma tail's structure with a clarity that chance rarely provides. A calendar that began as a shield becomes a blueprint for learning. By the time the visitor has faded, the calendar will look like a gridded tapestry, its coloured bands turned to pale notes. The usefulness of those notes lasts longer than the event they described. They become templates for any future object with similar dynamics. They teach that geometry governs risk more than drama does, that hours and angles matter more than headlines, and that a civilization can greet a stranger with both caution and composure by drawing its sky into time and then following the drawing exactly. Eyes gather from across the spectrum and from across the Earth, each tuned to a different sentence the visitor might speak. Space telescopes listen where air is loud. Ground telescopes listen where mirrors can be larger and nights are longer. Radio arrays count molecules by the music of their rotations, and small instruments scattered under domestic skies fill gaps no flagship can touch. Coordination is the instrument behind all instruments. It knits brief opportunities into a single portrait. Infrared light goes first. A cold nucleus wrapped in a warm coma writes its confession above 4 microns, where carbon dioxide vibrates with a clear signature. A cryogenic observatory isolates that band cleanly, peering through filters and grisms that separate dust continuum from gas features. Near-spec draws slits across the coma, stepping outward to map how production changes with distance from the nucleus. Near-cam images through tailored filters that bracket key bands turning chemistry into color. Mirae, deeper still, weighs thermal emission from grains and traces how their temperatures fall as sunlight releases them. Together, these data trace not just what molecules are present, but where they turn to wind, where they carry dust, and how quickly the warm breath fades to silence. Ultraviolet follows with a different alphabet. Hydroxyl near 308 nanometers stands proxy for water, and atomic oxygen glows green and red where photochemistry is at work. A wide UV spectrograph can place a long slit across the coma and measure the falloff of these lines, converting brightness to column density and then to release rates with models that honor scattering, quenching, and solar line pumping. The point is not a single number but a radial profile, a way to learn whether a few vents dominate or whether many small sources whisper together. Time series in the UV pin down outbursts that infrared eyes might miss when dust brightening hides narrow gas lines. Optical polarimetry turns scattered sunlight into a tactile measure of texture. Polarization rises and falls with phase angle and grain size, and its plane rotates when jets bias the near field. Multi-aperture polarimetry, sampling rings from hundreds to thousands of kilometers around the photocenter, reveals whether grains grow or shatter as they drift. It also reveals when fresh material appears, because young grains often polarize light differently from grains tanned by radiation. A night of clean polarimetric curves can diagnose a grain-size distribution without needing a single resolved pebble. Millimeter and submillimeter arrays count molecules that cannot be weighed by light alone. Rotational lines of carbon monoxide, formaldehyde, methanol, and other organics fall into quiet radio windows. With baselines stretched across desert plateaus, synthesized beams map the inner coma at scales where individual jets blur but families of jets can still be separated. Line profiles tell flow speeds and temperatures. Isotope log ratios hint at the history of chemistry before assembly, a memory older than any surface. Interferometers also have the virtue of filtering out smooth dust emission, leaving only structured gas behind. High-resolution optical spectroscopy plays a compact but decisive role. A shell spectrographs pry apart oxygen lines that overlap in coarse instruments, permitting the green-to-red ratio to be measured with honesty. That ratio, compared across apertures and nights, assigns credit for oxygen to water or to carbon dioxide, and closes loopholes left by blended features. At the same time, sodium and potassium lines, if present, mark dust sputtering and provide a barometer for how hard radiation and micrometeoroid impacts are working on grains in flight. Images large and small map morphology with shared discipline. On big apertures, adaptive optics tightens the point spread function and reveals inner jets as faint fans, arcs, or spiral traces that follow rotation. On modest telescopes under steady air, long stacks recover the faintest isophotes, those outward wings where hazard budgets live. Each stack is built on tracking that holds the moving target, letting stars trail into arrows that confirm the rate and protect against false centroids. A global cadence lets patterns emerge that no one sight could catch. A lobe that brightens when a particular longitude faces sunlight, a tail that kinks when solar wind sectors flip, a sunward wedge that swells only at small phase angles. Plasma is watched indirectly and directly. Heliospheric images aboard inner system probes capture white light from electrons that pile around dust and ions, tracing the plasma tail at scales too broad for narrow fields. In situ, monitors sample solar wind properties upstream, providing context when disconnection events sever and regrow the ion tail. When geometry places Earth behind the coma, long-wavelength radio networks test for scintillation and phase wander, adding practical constraints for deep space communications planning. Astrometry remains the metronome. Sub-arc-second positions measured against dense star catalogues feed orbit fits that permit and correct for non-gravitational terms. To curb coma bias, observers adopt tiny apertures, deconvolve when seeing allows, and propagate centroid uncertainties honestly. With each week of data added, ephemerides tighten, and the shapes of dust sheets are forecast with the confidence needed to schedule crossings or to avoid them. Occultations promise a different kind of precision. When the moving point is predicted to pass in front of a star, small telescopes along a narrow path time the dip. Several chords across the shadow sketch the silhouette of the inner coma. If lucky, a sharp central event betrays the nucleus itself, setting an upper bound on size that imaging cannot provide. Such events are rare and often faint, but they reward community networks that can mobilize quickly across continents. Laboratories complement the sky. Vacuum chambers cool mixtures of water, carbon dioxide, and organics to cryogenic temperatures, then warm them under solar analog lamps. Sensitive balances measure mass loss as a function of depth and time. Cameras record fracture patterns as rinds fail. Gas chromatographs trace which species escape first. These experiments do not mimic a comet in every detail, yet they calibrate the models that invert spectra and light curves into physics on and beneath the surface. Parameter ranges shrink. Plausible interiors become more specific. Data assimilation binds all of this. Thermophysical models ingest light curves, spectra, and images to infer active fractions, thermal inertia, and vent latitudes. Dust dynamics codes turn production rates into isophote maps, which are compared directly to deep stacks to refine grain-size distributions. Orbital solvers accept non-gravitational terms derived from gas modeling, closing a loop between chemistry and mechanics. Machine learning classifiers, trained on synthetic images that sweep across parameter space, offer fast triage for nightly morphology, so that the rare and the routine are separated before precious time is spent. Operations live inside constraints. Some space observatories keep solar arrays within strict angles and refuse pointings near bright planets. Campaign planners weave around these rules to catch the right phase angles for polarimetry, or the right geometries for antitails. High-altitude radio arrays pause for weather that leaves the sky pristine to the eye but hostile to millimeter waves. Backup nights are banked. Ground instruments facing moonlight adjust by narrowing slits, switching to line work less sensitive to glow, or handing schedules to southern partners under a darker moon. The choreography is mundane and heroic at once. Safety threads through the plan without drama. When deep imaging predicts a dense dust sheet on a given date, space assets postpone crossings or rotate sensitive faces away for hours. When UV lines climb suddenly, suggesting a burst that might loft coarse grains, cadence increases and hazard maps widen. When rotation rate drifts faster than thresholds allow, telescopes adjust to watch for fragments that might temporarily populate space near the nucleus. These responses are procedural, drafted in quiet meetings long before need arises. Citizens, under backyard domes, hold a vital strand. Their telescopes, modest in aperture and generous in time, fill longitudinal gaps, test cadence ideas, and extend light curves beyond what professional cues can supply. Shared calibration frames and agreed comparison stars make their work interoperable. In return, they receive ephemerides refined by large facilities and access to analysis scripts that turn their images into numbers that matter. The sky becomes a cooperative, not a hierarchy. All these instruments, earthly and orbital, chemical and mathematical, function as one body with many senses. They press against the frost with light and logic until the cold gives up its delicate secrets. The gain is not only knowledge of a single traveller, the gain is a pattern for the next one. A demonstration that coordination can turn short opportunities into lasting understanding, and that careful looking can keep both curiosity and hardware safe while the cosmos conducts its patient experiments in ice and sunlight. The computers begin with silence. Into that silence they pour guesses that are not guesses at all, but carefully drawn ranges. Nucleus size within an interval, bulk density sketched from cousins. Volatile mix arrayed as a menu of plausible ratios, spin states distributed across a narrow plaza of periods and pole tilts. Each element is a card in a deck. The model shuffles the deck thousands of times and lays out a universe of little worlds. A single visitor becomes an ensemble. and the ensemble is asked to suffer the unthinkable so that others will not. First, a fracture set in motion by heat and torque. A plate the size of a city block lifts and fails along ancient seams. The simulator assigns fragment sizes according to a power law and throws them into space with speeds picked from a distribution that respects escape velocity and jet drag. Radiation pressure is added grain by grain. Solar gravity is reduced by beta for each particle. The code breathes them forward along a hyperbolic spine, creating a ribbon that is not a metaphor but a map of where millimeter impacts would be felt if a spacecraft crossed carelessly. The ribbon thickens or thins across runs as the engine tries different vents, different times, different geometries. Next, an outburst at the ecliptic node. This is the worst place for dust to be born, because it feeds a sheet that lies close to where many vehicles travel. The simulations schedule the outburst at offsets of hours to days around the node and measure how the sheet deforms with the sun's light. Synthetic observers placed at L1, at L2, along transfer arcs to Mars, and on heliocentric orbits at varying inclinations, record particle fluxes by size. The team is not looking for catastrophe. It is looking for thresholds that move a plan from green to amber. When cached models predict affluence of millimeter grains likely to exceed the ballistic limit of a thin radiator, that hour is marked with a cross. The third branch explores a meteoroid stream that could graze a planet. The visitor's hyperbolic pace fights the formation of long-lived streams, but the ensemble allows for low probability tails, rare alignments where fragments released at the node disperse into a brief, fast rain months later. Synthetic radars on Earth, Venus, and Mars look up from the model and count echoes. Space stations and geostationary rings are given realistic cross-sections. A Poisson process sprinkles hits. None of the runs draws a sky thick with fire. A few draw sequences that would trip star trackers and ring fault logs the way hail rings tin roofs. The conclusion is modest. Possible, brief, manageable with warnings sent a few days early. Physics branches are woven into operations. For each fateful deck of cards, the simulator propagates uncertainties along with positions. Emission rates become covariances. Torques on the nucleus feed into spin state evolution, and that evolution feeds into the direction of jets which change the emission again. A slow Kalman filter ingests new measurements of brightness, slope, and oxygen line ratios and shrinks the cloud in parameter space where plausible futures live. Every shrink redraws the hazard map. The redraw is not cosmetic. It adjusts schedules for real instruments that will face a real sky. Hydrocodes take a turn when the model imagines slabs separating under pressure. They do not render art, they render stresses. A brittle foam architecture is given tensile strengths and floor distributions measured in laboratories where ices and dust are cooled until they hiss. Heat is applied from a virtual sundae. Pores open and close. When the arithmetic says yes, a sheet fails along a crack that chooses a path of least resistance drawn by the microstructure. The moment of failure defines ejector speeds for the smallest pieces and tipping speeds for the largest. Those numbers move to the next module, where dust dynamics track them outward, and to another, where spacecraft survivability tables wait. Survivability is written in equations that mission designers know by heart. Ballistic limit curves translate impact to size and velocity into probability of penetration for a given shield. The simulator lays a sheet of these shields over synthetic vehicles, one for an optical bench, one for a radiator, one for thin wall propellant lines, one for the face of a star tracker. Flux maps become risk maps. Risk maps become simple instructions. Rotate this panel away during these hours. Relax this instrument to a safe mode. Cross the sheet at a steep angle rather than along it. Add attitude deadbands so microglints do not cascade into false replanning. Plasma finds a place in the unthinkable, too. A strong carbon dioxide outflow feeds ions to a tail that can refract long-wavelength radio. The ensemble runs the solar wind through magneto-hydrodynamic models tuned by real space weather. It then inserts a synthetic ion tail and follows radio rays through it toward Earth. Phase wander and scintillation indices are computed for different geometries. If a deep space probe must uplink a critical file through that hour, the model prints a suggestion in plain language. Use diversity. Switch to a frequency less easily perturbed. Schedule repeats. Voyages through the ensemble are not left to the machine alone. Red teams run tabletop exercises with the maps projected on walls. A fragment ribbon crosses a planned path 3 days sooner than expected. What does the network do? Who calls which flight directors? What gets paused? And for how long? The answers are drafted into procedures that include numbers. How much the flux must rise before the plan flips state. How quickly a vehicle can rotate to present tougher faces. How many minutes it takes to return to nominal after the warning lamp goes dark. These procedures are published in shared portals alongside the evolving ephemerides, so that the response can be as distributed as the sky. Surrogates accelerate thought where full physics is too heavy for daily use. Neural nets learn the mapping from initial fragment speed distributions to flux levels at named waypoints. Polynomial chaos expansions approximate how uncertainty in one parameter changes the size of a hazard corridor. With these tools, the model answers "what if" in milliseconds instead of hours. Analysts type small changes and watch colored bands shift on a world map, a view that becomes a dashboard for those who must decide whether to hold course or trim. The simulator also tests for mischief by measurement. It injects biases into synthetic astrometry to learn how coma asymmetry can masquerade as an acceleration. It adds sky brightness gradients to synthetic images to see when a faint sunward wedge would be mistaken for an antitail. It lets the model fool itself, then teaches it to unlearn the error. These rehearsals prevent the worst unthinkable of all, that a false feature drives a real response. At the edge of possibility, the ensemble introduces a chain reaction scenario. A small outburst lifts fragments. A spacecraft crosses a thin part of the sheet and suffers a minor star tracker glitch. Safe mode triggers, and the schedule slips. The slip moves a planned crossing of a later, denser ribbon into the middle of that ribbon instead of the edge. The model evaluates whether a first inconvenience could magnify into a second. It then writes the antidote into the plan. Retain high-rate navigation even during brief safe modes when crossing dusty geometries, and prefer safe modes that maintain a minimum rate of sky sensing. Small choices undo big cascades. Communication is the bridge between model and world. Products are built with layers. The top layer is a simple calendar with colored days and hours, a mariner's chart for mission control. The middle layer is a set of flux curves by size with confidence bands, ready for engineers who need numbers. The lowest layer is the raw ensemble, offered to researchers who will hunt for rare but non-zero combinations that might still teach. Transparency replaces drama. Each user can trace a line from action back to assumption. Imperfection is acknowledged openly. The deck of cards is shuffled with priors that could be wrong. The model reminds its operators of that by holding back a fraction of the ensemble as wildcards that explore tales of distributions. Once in a while, a wildcard brushes against thresholds that the main cloud does not reach. Those brushes trigger searches for observations that would tell whether the tail should be promoted to the core or left in the margins. The instrument schedule adjusts. Time is bought for the measurement that could move a worry from maybe to not today. The unthinkable ends up looking ordinary in this light. A visitor sheds a sheet of grains. A ribbon forms along a line. A few windows in a long schedule are marked with caution, crossed at smart angles and smart times. Instruments listen to chemistry when geometry is friendly, and rest when it is not. The ensemble runs overnight and redraws corridors in the morning. The worst case is not a world-changing blow. It is a nuisance that becomes a lesson, because it was met with preparation rather than with surprise. This is how civilization practices calm. It simulates without panic, assigns numbers to worries, and converts the algebra of dust and light into page turns on a shared calendar. Out in the dark, a small body breathes. On screens filled with shifting color, the breath becomes a forecast detailed enough to protect a lens, and gentle enough to keep wonder intact. Word count 1197, awaiting un. Interception begins as a wish drawn on a chalkboard. A small craft waits in the quiet, its tanks full, its instruments asleep, its heat shield turned toward a sun it will one day dare. Somewhere beyond the orbit of Earth a stranger appears, faint and fast. The wish becomes a question of geometry and fuel. Can a sleeping scout wake, pivot, and meet a visitor that never slows? Two strategies divide the room. One is the ambush, a rapid redirection of an already flying spacecraft that can seize a narrow window. The other is the Sentinel, a patient platform parked where sunlight and stability meet, built to wait for years and then sprint. The ambush asks propulsion to conjure velocity on short notice. The Sentinel asks engineering to harden patience against time. The arithmetic is blunt. Interstellar visitors carry hyperbolic excess speeds of tens of kilometers per second. Any interceptor that starts near Earth inherits the planet's motion and still must pay a delta V bill that is not small. Chemical stages can deliver several kilometers per second in one breath. Electric thrusters can add more by grinding over months, but months are often what the sky refuses to grant. Solar sail fantasies dissolve when precision, mass, and the need to control attitude amid dust are counted. Nuclear dreams sit on shelves, impressive in slides, absent on pads. The boards fill with numbers that lead to a truth no one likes. Many apparitions will come and go before a bespoke chaser could even be stacked. The solar Oberth maneuver tempts the bold. Dive deep toward the sun. Burn at perihelion, where exhaust adds energy to a craft already moving very fast. Then slingshot outward on a new, steep curve that crosses the visitor's path. The glide path to such courage is narrow. Thermal protection must hold against heat that turns aluminum to fatigue in hours and paints the airless sky in infrared. Guidance must steer through a regime where control error translates to millions of kilometers at the far target. The prize is a jump in closing speed and a chance to shape the meeting. The price is the risk of a failure that leaves the interceptor on a useless arc with spent propellant and instruments cooked. Electric propulsion offers a calmer promise. High efficiency, fine control, gentle thrust integrated over long arcs. The problem is pace. The target's timetable is a season, not a decade, and the spiral outward that electric engines favor consumes the very time that would make their virtues relevant. Hybrid schemes are sketched, chemical to leave Earth's neighborhood swiftly, solar electric to trim the path, a final chemical dart to bend into the intercept. Each additional stage adds complexity, mass, and a fresh point of failure. The designs improve, then collide again with the calendar. Centuries rewrite the terms. Park a craft near the Earth-Sun, L2 point, or in an inner orbit where sunlight is strong and planetary shadows are infrequent. Keep it dormant, with batteries trickle-charged and gyros exercised on schedule. Give it a shielded camera to practice on comets, asteroids, and calibration stars so that, when the real call comes, autonomy is not a stranger. Equip a bus with a dust shield of layered bumpers that turn tiny bullets into clouds of harmless vapor. Add detachable probes, no larger than suitcases, each carrying a slab of aerogel and a small spectrometer, each able to peel off and dive through a coma on different chords. The Sentinel is not a single throw. It is a hand of cards you play in sequence. Navigation is the art that separates a dream from a mishap. Optical systems must lock onto a target whose head is a haze and whose tail confuses star trackers with streaming glints. The solution is a stack of modes that degrade gracefully. When the head is bright, track on a centroid sharpened by deconvolution. When the head fades or blooms, track on a predicted limb found by fitting a phase function to the coma. When everything flares, switch to inertial control while a short exposure camera blinks cadenced glimpses, enough to keep the filter alive until the star field returns. Communication with Earth becomes advice, not control. Minutes of light time turn commands into postcards. Autonomy must guide a craft through a crossing with a last course tweak taken hours earlier. Sampling at hypervelocity is a polite collision. Aerogel opens a path for grains to slow without shattering into plasma. Each track burned into the gel is a history of a single particle's size, speed, and composition. Shields ahead of the gel soften what the gel cannot catch. A narrow slot admits dust along a chosen vector. Cameras watch the flow of light for particles larger than the gel can tolerate and tip the craft a few degrees to miss small clusters the model did not foresee. All of this unfolds in seconds. The craft passes through a volume where the dust density climbs and falls like surf. On the far side, the instruments wake fully, check their own hearts, and begin to put numbers into solid-state memories that will not see home for days. Imaging is not the pursuit of pretty pictures. Fast shutters, freeze jets, spiral arcs, and stray against a background of street stars. A focal plane shielded from stray light measures gas bands with filters that bracket narrow features. Polarizers rotate to probe grain textures. The camera plan favors many short exposures over a few long ones, because a long exposure in a dusty sky is a negotiation with grief. The strategy is to assemble a mosaic in time as much as in space, then align the pieces using inertial sensors that never stopped writing. Whipple shields, the banal heroes of close work, do their part quietly. A thin bumper at the front turns an incoming grain into a spray. A spacing tuned to typical velocities gives the spray room to expand before it meets a second layer that absorbs what is left. The game ends at a rear wall that only a very unlucky particle reaches with enough energy to matter. Windows and radiators cannot hide behind such armor. Those are turned away during the sprint and brought back into view when the count says clear. Abort criteria are not admissions of defeat. They are proof that caution and ambition can share a cockpit. If a measured rise in inner coma brightness exceeds a threshold within an hour of crossing, if oxygen line ratios flip in a way that suggests a vent has opened where none was before, if charge monitors register a plasma surge that threatens to scramble star trackers during the minutes that matter most, the plan bends. The craft widens its pass, or turns a sub-probe into the primary sampler, or accepts a lower data rate in exchange for a geometry that keeps risks bounded. The goal is not heroic proximity. The goal is return. Why an intercept fails is often ordinary. Discovery comes late in the season. The node lies where burns are expensive. A relay is busy. An aging spacecraft that could have been redirected must instead preserve a proven mission that is not yet finished. Funding cycles do not pivot as fast as the sky. The chance passes. The chalkboard looks patient, but the craft cannot be everywhere. The phrase, the intercept that was not, is not a lament. It is an audit that lists how close the species came and exactly what stood in the way. Lessons gather in that audit. The surveys that find such visitors must warn earlier, which demands deeper cadence and faster pipelines. Standby craft must be real, not proposals. Parking orbits must be chosen not only for thermal comfort, but for branching angles that reach many inclinations cheaply. Small launchers with hot stages must be kept ready to throw shoebox scouts that carry a single instrument and a simple aim point. Collaboration must be pre-written, so that when one team sees a spike of oxygen in the dark, another team knows which hardware can catch the next breath. A future architecture begins to show its outline. One sentinel near L2, a second in a Venus trailing orbit, a third riding a modest solar orbit interior to Earth where Oberth burns cost less. Each carries microprobes. Each rehearses on ordinary comets. Each shares software, so that lessons migrate by code rather than by hope. On the ground, a desk in a quiet room keeps the calendar that marks windows across all three, and a single call tree knows whose phone will ring if an object appears, and the lines on the chart cross into green. Interception will remain an art of nearly. It will often miss, sometimes glancing by at distances that are scientifically rich and narratively unromantic, sometimes staying home because prudence said no. That is not failure. It is the world learning the tempo of fast visitors and tuning its instruments to that tempo. One day a craft will wake, burn at the right hour, cross a dusty sky at a right angle, and come away with a gel laced with tracks and cameras, filled with frames that show jets curling from a surface that no eye has seen. Until that day, the hand that reaches does not withdraw. It learns to wait, to measure, to plan, and to accept that patience is a kind of propulsion. Collateral arrives quietly in space. No alarms sound in the vacuum. No shock fronts ring through air that is not there. Yet a small body can lace the interplanetary lanes with subtleties that machines feel in ways humans might miss. The harm is seldom dramatic. It is a slow grit in bearings of procedure, a veil across optics, a twitch in the discipline of guidance. Each effect is modest. In combination, they test the margins that make exploration work. Dust is the first conspirator. Particles too small to threaten structure still throw sunlight into instruments that hunger for contrast. Star trackers that depend on patterns of pinpoints can be misled by a sudden field of sparkles. The cure is to raise thresholds, to demand more stars per solution, to slow the cadence of attitude updates while the sky is glittering. That cure costs precision, which then calls upon gyros to carry the load. Gyros are faithful but not eternal. Their errors grow with time. A flight computer that was meant to be casual becomes a careful judge of two imperfect witnesses, deciding whether to trust stars that may include imposters or to trust sensors that drift by design. Optical benches prefer clean glass. Hypervelocity dust does not grant that wish. A micrometer particle can pit a coating into a constellation of scatterers, faint but permanent. The next image acquires halos that were not in the budget. Exoplanet photometry, coronagraphy, and fine solar spectroscopy all depend on profiles sculpted to near perfection. When blemishes multiply, calibration can rescue performance only part way. Engineers respond with baffles and sacrificial windows that can be warmed to let volatile films depart, knowing that pits do not evaporate. The penalty adds up as a percent here and a percent there, small on paper, consequential when time on target is scarce. Solar arrays and thermal radiators face a different arithmetic. Tiny craters lower reflectance on panels and raise emissivity on radiators. Reflected light becomes heat less efficiently, and heat escapes into black faster than models predicted. The result is a shallow decline in available power and a subtle tilt in thermal balance that creeps into everything from battery charge margins to stability of optical structures. The drop is not a cliff, it is a slope. Missions ride it if planning is generous, and stumble if planning assumed pristine surfaces forever. Plasma plays its own games. An ion tail can be thin and still reach across lines of sight used by deep space radio. Long wavelength signals skimming the heliosphere collect phase wander and scintillation that look like the oceans seen through hot air. Ranging becomes noisy, Doppler becomes nervous. Error correction masks some of it, diversity in frequency and ground station geometry masks more, but windows appear when the smart move is to wait. Networks like to be busy. Waiting is a discipline that must be taught in advance. Charging is subtle until it is not. Surfaces in sunlight shed electrons and grow positive. Surfaces in shadow collect electrons and grow negative. In ordinary space weather, these gradients are managed by design. In a coma's plasma, local densities and temperatures change on scales of minutes and hundreds of kilometers. Differential charging across booms and solar wings can rise enough to arc at edges and connectors. Dust impacts add microplasmas that inject their own electrons, a peppering of tiny sparks against a field of slow drift. Most arcs are harmless. A few flip bits and reset subsystems that would not otherwise have blinked during critical hours. Navigation notices the collateral in a quieter way. Radiation pressure models assume optical properties that do not change quickly. Dust deposition and pitting alter both reflectivity and emissivity, changing how sunlight pushes and how heat leaves. The tiny accelerations that once matched expectations begin to stray. Orbit determination tightens tolerances. Thrust events are scheduled with wider margins. Propellant budgets absorb the extra burns that compensate for a cross-section shifted by grit. Ground telescopes are not immune to the visitor's fine debris and gas. Stray light from a dust sheet that sweeps near a field of interest can lift the sky by a few percent, just enough to erase the faintest lines in a spectrum. High-resolution imagers find ghost tails in their stacks when the guiding locks to a moving point and stars trail through dust. Meteor radars see a brief uptick in fast traces and must retune processing to avoid saturating near sunrise when daily sporadic streams are already busy. The sky does not apologize. Observatories adapt by scheduling line work at phases least infected by the extra continuum, by cutting narrower slits, by switching to modes that accentuate narrow features over broad. Spacecraft attitudes are chosen with care in such seasons. Sensitive panes are turned away during predicted crossings of faint dust wings. Radiators are given a chance to face colder skies. Star trackers are set to ignore transients shorter than a threshold that was drafted on a calm day for exactly this purpose. Some vehicles store alternate catalogues that exclude stars nearest the expected tail, so glints do not masquerade as valid points. Others switch to guide sensors shielded by thicker baffles, sacrificing sensitivity for resilience. Autonomy scripts wait like folded paper in a pocket, each to be opened only if a trigger moves from green to amber. Contamination is the patient cousin of damage. Outgassed organics can polymerize on cold surfaces, especially on instruments that choose to stay frigid to keep noise low. A fine film reduces ultraviolet throughput, muddles precise color calibration, and complicates the interpretation of any subtle spectral slope. Heaters built into optics defeat some of this by cooking away the film in controlled burns. Every bake resets alignment slightly, and the thermal steps must be walked with as much precision as the angles between stars. Planning reserve cycles for such housekeeping. Electronics carry their own vulnerabilities into the dust. A grain that vaporizes on impact creates a plasma cloud whose expanding edge carries a potential pulse into nearby wiring. Single event upsets, normally blamed on cosmic rays, can be seeded by such impacts as well. Most computers in space are hardened to tolerate flipped bits and restart without losing memory. The collateral risk lies in coincidence. A reset during a maneuver or a downlink that had no time reserved for a repeat. Operators stack redundant passes and keep critical sequences shorter and simpler while dust sheets are near. The penalty is tempo. Science slows to keep control tight. Environmental monitors turn nuisance into knowledge. Dust counters estimate flux by counting microphonics on panels and acoustic pings on shield coupons. Plasma probes record densities that tell how ions are born and lost. Magnetometers see the draping of field lines around a moving obstacle and trace disconnection events when sectors of the solar wind change sign. These sensors do not wait in laboratories. They are already flying on many platforms, and when a visitor passes, their data become a side channel that enriches astronomy with heliophysics. Worst credible collateral is an orchestration of small annoyances arriving together. A sheet of large grains passes a relay near a Lagrange point on the same day. A deep space probe must transmit a critical dataset through an ion tail that adds radio noise. The relay rotates to protect optics and loses a decibel of link margin. The probe's downlink sees scintillation and drops frames that cannot be reconstituted. A ground network that had booked every antenna must reshuffle, cancel a less urgent pass, and ask the probe to repeat hours later. No damage is done, a schedule ripples. People who planned ahead exhale, and people who did not learn that the sky cares little for pride. Mitigation is not mysterious. It is a handful of habits practiced consistently. Keep ephemerides fresh and hazard corridors wide. Cross-predicted dust planes at steep angles rather than skimming them. Store guidance catalogues that exclude fields near the projected tail. Prepare thermal cycles for optics. Schedule critical uplinks away from alignments that run through a plasma tail. Give autonomy scripts quiet authority to pause science and point tough faces outward for a few hours without waiting for a vote. None of this requires heroics. All of it requires attention paid early enough that the plan feels ordinary when it is needed. There is also the grace of turning risk into experiment. When a tail drifts near the line between Earth and a distant probe, dual frequency links can map the plasma with tomographic fidelity. When a dust wing strikes a satellite with a well-instrumented skin, the response logs become a calibration for shields and coatings that will fly later. When star trackers scatter glints into the sky, their false positives trace grain sizes that are otherwise inferred only indirectly. A season that complicates operations becomes a season that feeds models with numbers the clean sky rarely offers. Collateral in the vacuum is therefore not a threat that hunts drama. It is a reminder that the interplanetary medium is a real place with weather of its own. Machines that live there feel that weather first in whispers and only rarely in shouts. If attention is steady, the whispers inform rather than disrupt. An object passes on a fast curve. The sky brightens a little in unwanted places. A few panels collect scars too small to see from afar, and logbooks fill with notes written in a calm hand that begins, "Expected." The cosmos remains generous to those who prepare, and indifferent to those who do not. Worst case is a phrase that can be inflated by fear or sharpened by method. The sky accepts only the latter. To define it honestly, the uncertain is not banished. It is caged with numbers that refuse melodrama and still respect the edge cases nature favours. The practice begins by declaring what cannot happen, what could happen, and what is likely to happen if attention wanes. The first boundary is dynamical. A hyperbolic visitor enters and leaves, indifferent to capture. Orbital energy rules out impact and tidal shattering near worlds. That exclusion is not a comfort offered by hope. It is a structural fact that sets the stage for more modest, more relevant worries. The remaining risks live in gas, dust, plasma, and the small forces they exert on light, instruments, and schedules. The second boundary is geometric. Hazard concentrates in planes and sheets, not in spheres. Dust that leaves a vent does not fill space evenly. It organizes along the trajectory into a ribbon. It piles into a thin sheet where the path crosses the ecliptic. It forms faint wings that extend millions of kilometers, yet retain low densities. Worst case for machines is to skim these structures at shallow angles for long intervals. Honest planning converts that phrase into a rule. Avoid skimming. Prefer crossings steep in angle and short in time. Refuse alignments that stare along the sheet when critical operations are scheduled. The third boundary is chemical. Early activity driven by volatiles that wake before water creates long arcs of faint dust. Later activity driven by water can add sudden jets and torque. The extremes that matter are not explosions but inversions and surprises. A cautious envelope assumes that carbon dioxide begins the work far out and that water remains suppressed until late, then engages abruptly. Inside that envelope, two operational consequences appear. Large grains dominate the early sheet, so fluxes of millimeter to submillimeter particles define the mechanical risk. Small grains dominate late, so optical and thermal contamination define the sensing risk. The envelope is drawn wide at first, then narrowed by actual spectra and photometry. Non-gravitational forces provide the fourth boundary. Outgassing can move the body along track by tens to hundreds of kilometers over weeks, and cross-track by smaller but non-zero amounts. The honest worst case is not a tour through fantasy thrust. It is a bracketing of trajectories computed twice, once with conservative jetting terms and once without, and a promise that hazard corridors and instrument plans will respect both. If later astrometry squeezes the corridor, plans contract gladly. If weather steals nights, plans widen on paper before the sky forces the widening in reality. With those boundaries drawn, worst case takes the shape of specific thresholds. In the dust register, a conservative limit for safe passage near a sheet is not set by a single impact that might dent a panel, but by an integrated fluence that could saturate star trackers or compromise radiators. Numbers are assigned in design documents. The plan then connects observation to action. If inner coma brightness within a fixed aperture steepens beyond a preset slope, delay a crossing by hours. If polarization rises sharply at intermediate phase angles, assume fresh, coarse grains and widen margins around the sheet. If the tail's position angle jitters beyond a few degrees night to night, expect large fragments to bias the photocenter and consider the near field untidy for a short while. In the plasma register, worst case is a window of radio noise rather than a curtain of silence. The test is simple. If the ion tail lies near the line between a deep space transmitter and Earth, treat long wavelength links through that hour as at risk for scintillation. The response is equally simple. Use frequency diversity. Borrow time on a second ground station to alter the path through the heliosphere, and schedule repeats. No despair is required, only patience structured in advance so the wait does not ruin a mission clock. For optical instruments, worst case turns on cleanliness and contrast. Dust deposition that builds a film on cold optics will be slow, pits from micro-impacts will be rare, yet both change point spread functions. Honest planning assumes a % of throughput loss and a modest broadening of profiles if a vehicle must pass a dusty volume. Heated decontamination cycles are reserved on the schedule and the thermal steps are rehearsed. Science modes that are vulnerable to scattered light are moved off the calendar during predicted crossings and replaced by modes that value emission lines or polarimetric angles less sensitive to halos. Navigation has a quieter worst case. A sheet of small forces accumulates and the vehicle's cross-section changes as surfaces lose polish. Radiation pressure models drift from reality, and maneuvers miss by fractions. The antidote is already doctrine. Add tracking passes, keep delta V in reserve, and prefer 2 small burns to 1 bold burn when dust season begins. If a star tracker blinks during a crossing and hands control to gyros for a few minutes, the attitude solution does not surprise, because limits and timeouts were tuned on purpose to allow exactly that loss and recovery. For Earth orbit and the ground, worst case is a series of minor inconveniences arriving together. Meteor radars see a brief uptick in fast, faint echoes that must be sorted from daily backgrounds. Long integrations on telescopes are paused when a faint dust wing drifts through a field where the sky was expected to be clean. Spectrographs shift to lines best measured against raised continua. Deep space networks reshuffle a few passes to avoid the most warped plasma lines of sight. If calendars and scripts were written with these moves in mind, the night is remembered as busy but normal. Transparency in public communication is part of the honest definition. Worst case is not communicated as a cloud of anonymous alarms. It is framed as a list of triggers and responses. When brightness within a specified radius changes by a certain amount, a crossing moves by this many hours. When oxygen line ratios tip toward a particular parent, a guard band widens by this many days. When rotation period drifts faster than a threshold, a watch is declared for tiny fragments near the head. The list is the antidote to rumor. It keeps attention where it belongs, on numbers that behave and on responses that respect them. The sky does allow a wilder corner in the box. A slab could lift and populate space near the head with temporary companions. A spacecraft that must pass within a few thousand kilometers of the nucleus would then face targets too sparse to map, yet too large to ignore. The worst case here is avoided not by armor, but by refusing proximity that close for an uncharacterized interstellar body. Remote sensing remains rich at distances where fragments become background. Sample return ambitions stand down unless a sentry has mapped the dust thoroughly and the angles are favorable. Honesty also requires admitting where ignorance remains. If water refuses to rise when expected, or if it surges late, the torque budget and the dust budget can change quickly. The plan acknowledges this with belts and suspenders. Dust maps are updated nightly, and decisions that hinge on those maps are never locked earlier than data can justify. A small set of maneuvers is kept unassigned until late. Instruments that can pivot between riskier and safer modes retain that agility until the final hour. Worst case in this posture is reduced to a handful of late changes that feel routine because they were allowed for in design. Risk is never zero in a living sky. Honest worst case is the smallest set of unlikely but physically credible events that would still bend schedules and test margins. It is a fragment sheet that crosses a planned lane on an awkward day, a plasma tail that adds noise to a long hop of data, a cluster of glints that asks star trackers for patience, a thin film that requires a bakeout that was already planned. It is not a threat to lives or to worlds. It is a test of craft. To finish the definition, one more circle is drawn around responsibility. The line between worry and vigilance is maintained by cadence, by sharing, by writing procedures in plain language, and letting everyone who needs them read them early. With that culture, worst case hardens into a practice. A visitor passes. The numbers move within their bounds. People do what they said they would do when the numbers moved. The sky remains itself, indifferent, and the civilization beneath it remains calm, informed, and ready for the next small renegotiation between sunlight and ice. Sound does not travel in the vacuum, but rumour does. A faint smudge in a telescope becomes a headline, then a thread, then a cascade of small certainties stated too loudly. Words like interstellar, hyperbolic, and unknown collect adjectives as they move. In living rooms and classrooms, the same three questions circle the table. Will it hit us? Is it artificial? When can we see it with our eyes? Each answer wants a calendar and a map more than a flourish. Yet the human mind loves images that leap past numbers. The task becomes to give awe a shape that does not invite fear to occupy the same room. Communication begins with scale. An artist's rendering can turn a nucleus meters across into a mountain hanging over a skyline. A press release can compress millions of kilometers into a narrow phrase that sounds like arm's length. The remedy is visual honesty. Put a ruler on the picture. Place the Earth and the Moon as small circles far apart, and mark the path as a thread that does not come close. Draw the Sun as a disk and print the dates where the object will be at pleasing angles for observation. Then put a dot at the Earth with a label that reads too far for naked eyes. A single, clean figure slows the imagination into truth. Numbers must be simple to be useful. A forecast wins trust when it reports distances, dates, and brightness in round quantities with uncertainties that feel like humans could have measured them. 10 significant digits are embroidery, when a reader only needs the week and the order of magnitude. If probabilities are offered, they should be offered with a verb that speaks gently. Likely to remain faint is better than 92% in a sentence without context. Experts may ask for the raw tables. The public deserves sentences that weigh lightly, yet rest on the same bedrock. Uncertainty is not a flaw to hide. It is a boundary to colour in as data arrive. When an ephemeris changes, the update is best shown as a corridor narrowing rather than a path jumping. When a production rate is revised, present a small panel that shows what was measured, how the measurement changed, and what triggered the new conclusion. The phrase "we do not know" is not an embarrassment when it comes with when we will look and what will decide. Calendars stitched into these notices draw attention away from speculation and toward the next moment of truth. Rumour loves the appearance of secrecy. Open repositories disarm that love. Post the astrometry in a format that anyone can read. Provide the code used to fit non-gravitational parameters and the conditions under which it was run. Include changelogs that explain in 2 lines why a revision was made. Publish schedules for future observations with enough detail that citizens can aim their own telescopes. A rumour cannot compete with a place where readers can click and see the same numbers that guide the work. Speed in messaging matters, but steadiness matters more. A daily update at a known hour, even if it says little more than unchanged within uncertainties, soothes. A singular dramatic bulletin that lands weeks apart invites anxious gaps. When an outburst occurs, a brief note with a thumbnail image and 2 measured quantities arrives first, and a longer, reflective piece follows in a day. This rhythm respects curiosity, while it protects against the stampede that can start when words like explosive or sudden are attached to events that are in truth modest and bounded. Social traffic can be a weather system of its own. A term like plasma tail becomes communications blackout in a few enthusiastic retellings. A sentence about a dust sheet that might raise meteor counts by a whisper turns into showers. Moderation teams who sit close to the scientists and carry the numbers as they appear are part of the instrument suite. They answer with prepared phrases that are numerate and kind, and they carry links to the figure that frames the truth. They avoid combative tone and offer context patiently, then pin the calm language to pages that travel further than a correction left only in a comment thread. Institutions teach by the models they choose. A traffic light graphic that changes from green to amber to green again over weeks shows that caution can rise and fall without ever turning red. A forecast archive with scores that show how accurate the last season's predictions were turns confidence into a measurable thing. When models miss, a small box titled "What We Learned" sits beside the miss and lists 2 specific changes in procedure. In this way, trust becomes a ledger, not a performance. Fear is not only outside. It enters the room where decisions are made. A plan that was sound at the last meeting can feel fragile when a headline has run hot for a day. The correction is a checklist written before the sky grew noisy. It lists triggers tied to data, not to mood. If the inner coma brightness slope steepens past a chosen value, widen the schedule window. If the oxygen line ratio crosses a threshold that indicates a change in parentage, move a crossing by half a day. If rotation period drifts faster than expected, raise cadence for imaging. Each trigger points to an action that was agreed upon when minds were quiet. Education gives audiences the tools to be calm without being passive. A short video that explains why a hyperbola does not close and what V infinity means will travel farther than a paper. A classroom kit with an activity where students plot a path on graph paper using 3 points and watch a fourth land near the prediction creates a generation less vulnerable to the seductions of ominous words. Outreach that invites small telescopes to contribute light curves with shared comparison stars creates citizens who feel agency and therefore suspicion toward rumor. There are darker corners to the human echo. Personal abuse falls on visible scientists when a rumor has been contradicted. Harassment flares when an answer is not the answer a fervent audience wanted. Institutions prepare moderators for this too. They post codes of conduct, ban with documentation when needed, and give staff breaks from public channels so that no voice is overused. They remind themselves that kindness in response does not demand tolerance of harm, and that the work is better when the people doing it are protected. Newsrooms benefit when they are offered assets that do not invite nonsense. Provide high-resolution images with honest scale bars. Offer animations that move at real time or with labeled time compression, not clips that make a slow arc look like a sprint. Supply quotes that speak of limits and of wonder without implying either drama or indifference. Place a phone number and an email that will be answered within hours by someone who can say on the record what the numbers actually mean. Journalists often want to get it right. The easier that path is, the more likely the story is to retain its proportion as it walks from domain to domain. Language should not borrow dread from fiction. Words like encounter and intercept belong in specific, technical contexts. Words like threat and danger belong in guidance that lists planned responses, not in headlines that trade in sensation. Equally, language should not pretend that nothing ever happens. It should celebrate clean measurements, crisp geometries, and careful maps. The middle register, where respect and clarity meet, is the place where a culture grows less prone to panic each time the sky presents something rare. Transparency is not a guarantee against noise, but it changes the ratio between noise and signal. When data are posted, methods shared, thresholds pre-declared, and schedules maintained, fear finds less to grip. What would have been an anxious week becomes a patient sequence of small updates. What would have been a myth about a machine becomes a paragraph explaining how the light curve resists the signature of mirrors. What would have been a worry about a blackout becomes a note about scintillation along long wavelength links and the plan to repeat the past later. A traveller from far away cannot shape its own narrative. People do. If they choose spectacle, the narrative grows teeth it does not deserve. If they choose calm detail, the narrative becomes a room with windows where the public can walk in and look out. The human echo can amplify fear or understanding. It can be a chamber where panic rebounds until it feels like truth, or it can be a hall where quiet facts are repeated until they feel like a common language. The choice is daily. The better choice is simple. A small visitor leaves more than a curved line on a chart. It leaves an inventory of virtues that a thoughtful species can keep. Patience becomes the first item. The sky rarely hurries, and when it does, panic cannot help. Patience looks like cadence that does not falter, like instruments that return each night to the same task until the noise gives up its secrets. From patience flows precision, the habit of measuring what is there rather than what is feared. Precision is the courage to let uncertainty shrink only when the data allow. Together, those two habits turn mystery into maps. Knowledge expands in three directions at once. At the surface, chemistry acquires texture. Ratios that once seemed fixed now arrive as ranges, and those ranges describe real places where worlds are built. Deeper down, engines made of pores and shadows become models that run cleanly because they are forced to face numbers. Outward into space, dust no longer plays the role of ornament. It becomes a medium with weather. Sheets, ribbons, filaments, and faint wings are taught by images until they are taught by instinct. The vocabulary of that weather then becomes a language for safety. Technology learns to prefer readiness over heroics. Sentinels that wait in useful orbits gain purpose. A compact bus that can wake fast becomes a kind of discipline turned into hardware. Aerogels that once seemed quaint are cut to new shapes. Shields are thickened along lines that particle models draw. Guidance modes practice failing gracefully while still returning science. Each upgrade feels small on a whiteboard, then large in the quiet minute when a glint-crowded star tracker needs a fallback already rehearsed. Institutions are changed as much as instruments. Schedules are written with shaded corridors rather than hard walls. Triggers are published in plain words so that decisions feel inevitable when numbers cross them. Shared pipelines accept strangers because strangers may stand beneath clear air when a flagship dome is closed. Archives open by default. Confidence becomes measurable because forecasts are saved and graded later. In that culture, rumor loses its power. People learn to wait for the hour, when the corridor narrows and the plan adjusts without fuss. Education bends toward participation. Light curves gathered from backyards join stacks from mountaintops. A student learns to fit a conic and finds joy in the moment when prediction meets the next point. A class plots a tails angle night after night and watches the sun write physics in a language teenagers can read. These small acts recalibrate attention. A public that contributed does not need to be convinced with grand phrases. It recognizes the look of uncertainty that is honest. It knows how to live with it. Heliophysics and planetary science discover a shared frontier. Ion tails become laboratories for the solar wind, and radio links that wander become tomograms that map plasma in 3 dimensions. Dust sheets that disturb star trackers become calibrations for the next coat of armor. The same event that complicates operations grants experiments that would have been too expensive to stage. An economy of curiosity emerges, in which risk is traded for understanding in measured steps rather than gambles. The future receives a blueprint that is conservative and brave at once. Surveys deepen cadence and tie their clocks together across hemispheres. Watch lists for the rare are maintained without drama. One craft waits near a friendly Lagrange point, a second along an inner orbit where sunlight is strong, a third in rehearsal around a familiar comet to perfect the art of passing through dust without flinching. The blueprint asks for coordination rather than spectacle. It is modest because modesty is what works. Philosophy follows the instruments. Wonder keeps its place but wears a quieter coat. It becomes the respect shown to small forces measured carefully. It becomes the decision to communicate thresholds instead of feelings. It becomes the refusal to tell a scary story when a true one is available and sufficient. Fear is not the opposite of wonder. Neglect is. Attention practiced for its own sake is the way a species remembers that the cosmos rewards care. The visitor teaches that a worse case should be both honest and dull. Honest because physics deserves clarity. Dull because preparation drains drama of its power. The most credible hazards are avoidable annoyances when calendars are drawn correctly, when crossings are steep, when equipment expects glints, when links expect scintillation, when heaters are ready to bake a film from a lens and then step back to a set point without warping a mount. The lesson is not a chant of safety first. It is the quieter claim that science is safer when it is more exact. Finally, the curve itself is a teacher. A hyperbola is an act of refusal. It says that not every path returns. It also says there will be another chance in a different year, under a different geometry, with a different chemistry that will ask for slightly different tools. The vow worth making is simple. Keep the tools ready. Keep the calendars honest. Keep the language plain. Meet the next traveller with eyes that love detail more than drama, and with hands that know how to turn detail into care. What remains is gratitude for a lesson written in frost and light. A small body crossed a big system and did not know it was teaching. People noticed, listened, argued carefully, and changed how they will look next time. That is the work. That is enough. Night folds the chart and keeps the stars. A thin question fades along a path that will not be walked again. No trumpet marks the moment. A whisper of dust drifts into dark where sunlight will not follow, and a little world returns to exile. That is not exile at all, but simple distance. In the rooms where screens still glow, maps rest with their coloured corridors turned pale. Instruments cool, minds cool. The echo of numbers lingers like the afterimage of a bright line when eyes are closed. He stands nowhere, she stands nowhere, they all stand nowhere, because standing is an earth word. Still a posture is felt. It is the posture of attention practiced until it becomes quiet joy. The visitor taught no creed. It turned no key. It allowed the living to front their curiosity with steadiness, and in that steadiness they met themselves as well as the sky. A single curve was enough. Frost will find other suns. Engines of pause will whisper again. Dust will draw sheets so thin they seem imagined. People will be ready with slower hearts and better clocks. They will have learned that risk is only the negative space around care, and that awe is a craft when it is not a shiver. A last photon leaves a grain in flight and spends its gift across space into a lens held open by a plan. It arrives as a number. It becomes a sentence. It becomes a kept promise to look with kindness, to measure without haste, to speak plainly, to greet the next stranger not with fear, but with a steady hand.